Hey everyone, tonight we're stepping into a world so alien, so impossibly ancient, that it makes science fiction look mundane. Picture this: a planet where the very concept of death as we know it didn't exist, where organisms grew like living fractals across the seafloor, and where the first ecosystems emerged from conditions so extreme they'd instantly kill every living thing on Earth today. Welcome to the Ediacaran period, roughly 635 to 541 million years ago, when our planet conducted its first grand experiment in complex life. Now, before we dive headfirst into this prehistoric wonderland, take a moment to like this video if you're ready for a journey that'll completely change how you think about life on Earth. And let me know in the comments where you're watching from and what time it is for you. There's something oddly comforting about knowing we're all here together, exploring the deep past while scattered across the present. Dim those lights, grab your favorite drink, and settle in. Because what we're about to explore isn't just ancient history. It's the foundation story of every ecosystem that has ever existed, including the one you're sitting in right now. The Ediacaran period holds a special place in the history of our planet. It was officially recognized as a geological period only in 2004, making it the first new period declared in 120 years. Think about that for a moment. We've been studying Earth's history for centuries, mapping every rock layer and fossil bed we could find. And yet this entire chapter of life's story was so strange, so unlike anything that came after, that it took until the 21st century for scientists to fully appreciate what they were looking at. Named after the Ediacara Hills of South Australia, where geologist Reg Sprigg first discovered these bizarre fossils in 1946, this period represents something unprecedented in Earth's history. The rise of the first true ecosystems. Not just individual organisms struggling to survive, but interconnected communities of life forms that worked together, competed with each other, and transformed their environment in ways that would echo through the next 500 million years. But here's what makes this story so compelling. The Ediacaran period didn't emerge from some gentle, gradual warming of ancient seas. No, it exploded into existence in the aftermath of the most extreme climate catastrophe our planet has ever endured. We're talking about Snowball Earth, a time when ice may have extended all the way to the equator, freezing the entire planet into a crystalline tomb. Imagine waking up one morning to find that every ocean on Earth had turned to solid ice, that glaciers stretched from pole to pole, and that the only liquid water existed in rare pockets deep beneath the frozen surface. That was the world just before the Ediacaran began. The Cryogenian period had subjected Earth to not one, but two massive glacial events called the Sturtian and Marinoan glaciations. Each lasted millions of years, and each came terrifyingly close to ending the story of life before it had really begun. The Marinoan glaciation, which ended approximately 635 million years ago, marked the boundary between the Cryogenian and Ediacaran periods. As those massive ice sheets retreated, they didn't just reveal a planet ready for life to continue as it had before. They revealed a planet transformed, with ocean chemistry, atmospheric composition, and environmental conditions unlike anything that had existed previously. The thawing of Snowball Earth triggered a cascade of changes that would prove crucial for the evolution of complex life. Oxygen levels rose dramatically in both the atmosphere and oceans. The oxidation of dissolved organic carbon in marine environments created new chemical gradients and energy sources. Most importantly, the retreat of the ice revealed vast expanses of shallow, nutrient-rich seas that would become the nurseries for Earth's first complex ecosystems. But the environmental changes weren't limited to climate recovery. The Ediacaran period witnessed some of the most dramatic tectonic upheaval in Earth's history. The supercontinent Rodinia, which had dominated the planet's geography for millions of years, was breaking apart in a spectacular display of geological violence. Massive rifting events split continents, creating new ocean basins and flooding enormous areas with shallow seas. As Rodinia fragmented, a new supercontinent called Pannotia began to form, centered near the planet's south pole. But Pannotia was geologically restless, beginning to break apart almost as soon as it had assembled. By around 550 million years ago, it had split into the continental blocks that would become Laurentia, Siberia, Baltica, and the massive southern supercontinent Gondwana. All this tectonic activity wasn't just reshuffling the planet's surface features, it was creating the environmental conditions necessary for complex ecosystems to emerge and thrive. Volcanic activity associated with continental breakup pumped nutrients into the oceans. The formation of new ocean basins created diverse marine environments with different temperatures, depths, and chemical compositions. Shallow seas expanded across continental shelves, providing vast areas of habitat where early life forms could experiment with new ways of living. The most crucial change, however, was the transformation of ocean chemistry, particularly regarding oxygen availability. For billions of years, Earth's oceans had been largely anoxic, containing little to no dissolved oxygen. But during the Ediacaran, something remarkable happened. The oceans became fully oxygenated for the first time in the planet's history. This wasn't a simple, uniform process. Research has revealed that different regions had vastly different oxygen levels, creating a complex mosaic of habitable and inhospitable environments. Some areas remained anoxic or even toxic, while others became rich in the oxygen that complex life forms would need to power their metabolisms. The relationship between oxygenation and early animal evolution was more nuanced than scientists initially thought. Recent research has shown that anatomically simple organisms, particularly sponges, could survive under very low dissolved oxygen levels. This suggests that the availability of oxygen wasn't just about providing breathable conditions for early animals. It was about fundamentally altering the chemistry of the oceans and enabling entirely new types of ecosystems to exist. What made this oxygenation event so significant was its interaction with the biological innovations that were emerging at the same time. The foundation of these new ecosystems wasn't built on large, charismatic organisms that we might recognize today. Instead, it was constructed on something far more humble but equally revolutionary: microbial mats. Microbial mats had existed on Earth for billions of years, but during the Ediacaran period, they reached unprecedented complexity and diversity. These weren't simple bacterial films coating the seafloor. They were sophisticated, multi-layered ecosystems in their own right, consisting of different communities of microorganisms arranged in distinct layers according to their metabolic requirements and chemical tolerances. The greatest diversity and complexity of organic mat textures in the entire fossil record occur in rocks of Ediacaran age. These mats were typically only a few centimeters thick, but within that narrow space, they created an incredible range of internal chemical environments. Oxygen-producing cyanobacteria dominated the upper layers, while sulfur-reducing bacteria thrived in the deeper anoxic zones. Between these extremes, dozens of different microbial communities carved out their own specialized niches. But these microbial mats weren't just passive carpets covering the seafloor. They were active ecosystem engineers, creating the environmental conditions that would make complex life possible. The mats stabilized sediments, preventing erosion and creating stable surfaces for larger organisms to attach to. They generated oxygen through photosynthesis, creating localized pockets of high oxygen concentration that could support early animals with limited metabolic capabilities. Research on modern microbial mat systems has revealed just how dramatic this localized oxygenation could be. Studies of contemporary mats in places like Los Roques Lagoon in Venezuela have shown that oxygen concentrations within the mat can be 4 times higher than in the surrounding water column. For early animals struggling to extract enough oxygen from their environment, these mat systems would have been like oases of breathable air in an otherwise hostile world. The mats also provided crucial mechanical support for early organisms. Many of the upright, frond-like creatures that would come to dominate Ediacaran ecosystems anchored themselves either into the sediment or beneath the microbial mats. The sticky, cohesive nature of the mats helped stabilize these attachments and may have been essential for allowing large, complex organisms to establish themselves in marine environments. Perhaps most importantly, the widespread presence of microbial mats aided in the preservation of the fossils that allow us to study this ancient world today. The mats help stabilize impressions of soft-bodied organisms in the sediment below, creating the exceptional preservation conditions that have given us our window into Ediacaran ecosystems. Into this world of oxygenated seas, tectonic upheaval, and microbial innovation came the stars of our story, the Ediacaran biota. These were Earth's first complex multicellular ecosystems, and they were unlike anything that had existed before or has existed since. The predominant organisms were soft-bodied, invertebrate forms that predated the famous Cambrian explosion by tens of millions of years. The diversity of these ecosystems was remarkable. Scientists have described around 200 species of large organisms from the Ediacaran period, representing an explosion of biological innovation that rivals any other period in Earth's history. Fossils of these characteristic Ediacaran animals have been excavated from more than 30 locations on every continent except Antarctica, indicating that complex ecosystems had emerged on a truly global scale. But the Ediacaran biota didn't exist as a single, uniform community. Instead, these early ecosystems evolved through 3 distinct phases, each representing different stages in the development of complex life and different environmental conditions. The story begins with what scientists call the Avalon explosion, approximately 575 to 565 million years ago. This represents the first major radiation of complex, multicellular life on Earth, and it happened in some of the most unlikely conditions imaginable. The organisms of the Avalon assemblage lived in deep, cold ocean environments, far from sunlight and the warmth of shallow seas. The Avalon assemblage is best known from Mistaken Point on the Avalon Peninsula of Canada, where exceptional preservation conditions have given us exquisite details of these ancient ecosystems. The site contains numerous fine ash beds that not only provide excellent material for radiometric dating, but also preserve incredible detail of the organisms that lived there. The dominant life forms of the Avalon explosion were the rangermorphs, some of the most alien organisms ever to inhabit our planet. These creatures looked roughly like fern fronds or feathers arranged around a central axis, but their internal structure was based on principles completely foreign to modern biology. What made rangermorphs truly unique was their fractal architecture. These organisms were built using self-similar, repeating patterns at multiple scales. The entire body was formed of branching sections, and each section repeated the same shape as the whole organism. Each major branch was composed of smaller branches, which were in turn composed of even smaller branchlets, all following the same basic architectural plan. This fractal body plan wasn't just an aesthetic curiosity, it was a sophisticated solution to the problem of how to maximize surface area for nutrient absorption while maintaining structural integrity. Using mathematical models based on formal fractal systems, scientists have shown that rangermorph morphology represents an optimal strategy for extracting nutrients from the water column through direct absorption. The most thoroughly studied rangermorph is Charnia masoni, perhaps the most iconic member of the entire Ediacaran biota. Charnia was first discovered in Charnwood Forest in England, and represents a crucial breakthrough in our understanding of pre-Cambrian life. When it was first described in 1958, Charnia provided the first unquestionable evidence that complex multicellular organisms had existed long before the Cambrian period. Recent advances in imaging technology have revealed the sophisticated internal organization of these remarkable creatures. X-ray tomography and computed tomography of rare three-dimensionally preserved specimens have shown that Charnia possessed a highly connected and compartmentalized internal architecture. The organism was constructed of repeated branches that derived successively from pre-existing branches, creating a hierarchical network of internal connections. This internal complexity suggests that rangeomorphs were far more sophisticated than their simple external appearance might suggest. They possessed developmental regulatory machinery that allowed them to construct and maintain their fractal architecture with remarkable precision and consistency. Another fascinating rangeomorph, Fractofusus, has provided evidence for sophisticated reproductive strategies in these early complex organisms. Fossil evidence suggests that Fractofusus was capable of both budding, where new individuals developed from generative points on the parent organism, and releasing waterborne propagules that were genetic clones of the parent. Clones of the parent. This ability to switch between reproductive strategies reveals just how sophisticated these early ecosystems had become. The fact that organisms like Fractofusus could adapt their reproductive methods to environmental conditions suggests a level of biological complexity that scientists are only beginning to appreciate. Some individuals would lie flat against the seafloor, while others projected upward into the water column, creating a three-dimensional community structure as they competed for nutrients and energy sources. The success of these fractal pioneers wasn't just about individual survival. They were creating the first truly complex ecosystems, with different species occupying distinct ecological niches and interacting with each other in ways that transformed their shared environment. The rangeomorphs dominated the deep, cold waters of the early Ediacaran, but they were just the beginning of a biological revolution that would reshape the planet. As we move forward in time, around 560 million years ago, the Ediacaran story takes another dramatic turn. The deep water environments that had nurtured the rangeomorphs began to give way to shallower, warmer seas. This transition marked the beginning of the White Sea assemblage, named after the region in northwest Russia where many of these fossils have been found. The White Sea assemblage represents the peak of Ediacaran diversity and ecological complexity. Unlike the relatively uniform communities of the Avalon explosion, these ecosystems were characterized by an incredible variety of body plans, feeding strategies, and ecological relationships. This was the golden age of the Ediacaran world, when biological innovation reached its zenith and created ecosystems of unprecedented sophistication. One of the most significant developments during the White Sea period was the evolution of organisms with fundamentally different approaches to obtaining energy. While the rangeomorphs had relied primarily on absorbing dissolved nutrients from the water column, the new organisms of the White Sea assemblage began experimenting with more active feeding strategies. Enter Dickinsonia, perhaps the most famous and controversial organism of the entire Ediacaran period. For decades, scientists debated whether Dickinsonia was an animal, a plant, a fungus, or something else entirely. These oval-shaped creatures, which could grow up to a meter in length, dominated many White Sea communities and left behind some of the most beautifully preserved fossils in the entire geological record. The mystery of Dickinsonia's biological identity was finally resolved in 2018 through one of the most remarkable scientific detective stories in paleontology. Scientists collected samples from exceptionally well-preserved Dickinsonia fossils in the White Sea region of northwest Russia and subjected them to cutting-edge biochemical analysis. What they found changed everything. The fossils contained an abundance of cholesterol molecules, up to 93% of the organic compounds present. Cholesterol is a biomarker that is produced exclusively by animals, providing the first definitive proof that Dickinsonia was indeed an early animal. The surrounding seafloor sediments, in contrast, contained ergosteroids, characteristic of green algae, confirming that these organisms lived in a world dominated by microbial communities. But Dickinsonia wasn't just any animal. Recent research has revealed that these creatures were mobile, capable of moving across the seafloor in search of food. Fossil trackways show evidence of Dickinsonia gliding over microbial mats, apparently grazing on the rich communities of microorganisms that carpeted the seafloor. This represents one of the earliest examples of active feeding behavior in the animal kingdom. The feeding strategy of Dickinsonia was remarkably sophisticated for such an early animal. These creatures appear to have been capable of both external digestion and nutrient absorption. They would settle over patches of microbial mat, release digestive enzymes to break down the organic material, and then absorb the nutrients through their ventral surface. After depleting the resources in one area, they would move on to fresh feeding grounds, leaving behind distinctive feeding traces in the fossil record. This mobile lifestyle represented a revolutionary departure from the sessile existence of the rangeomorphs. Dickinsonia and its relatives were among the first organisms to actively modify their environment through their feeding activities. By grazing on microbial mats, they created a feedback loop that influenced the distribution and composition of these fundamental ecosystem components. The White Sea assemblage also witnessed the emergence of organisms with entirely new body architectures. Alongside the familiar frond-like forms and the mobile discoidal creatures like Dickinsonia, this period saw the evolution of organisms with radial symmetry, bilateral symmetry, and complex branching patterns that defied easy categorization. Sprigina, named after the discoverer of the Ediacara Hills fossils, represents one of the most intriguing examples of this morphological experimentation. This segmented, worm-like creature possessed what appears to be a distinct head region and showed clear bilateral symmetry. Some scientists have suggested that Sprigina represents an early experiment in the body plan that would later give rise to arthropods, though this interpretation remains controversial. Tribrachidium, another White Sea organism, took a completely different approach to ecosystem participation. This small, disc-shaped creature possessed threefold radial symmetry, a body plan that has never been successfully repeated in the subsequent history of life. The organism appears to have been sessile, anchored to the seafloor, with three curved ridges radiating from a central point. The function of these ridges remains mysterious, but they may have been involved in filter feeding or in directing water flow for respiration. The diversity of feeding strategies during the White Sea period was truly remarkable. While some organisms like Dickinsonia actively grazed on microbial mats, others appear to have been suspension feeders, extracting nutrients from the water column. Still others may have been osmotrophic, absorbing dissolved organic compounds directly through their body surfaces. This ecological diversification wasn't happening in isolation. The White Sea ecosystems were characterized by complex interactions between different organism types, creating the first multi-tiered communities in Earth's history. Tall, frond-like organisms reached up into the water column, competing for space and nutrients with their neighbors. Mobile forms moved across the sea floor, modifying the substrate and creating new opportunities for other organisms. Sessile forms anchored themselves to stable surfaces, filtering the water and processing nutrients in ways that influenced the entire community. The preservation of these ecosystems provides us with unprecedented insights into the ecological dynamics of early complex life. Fossil assemblages from the White Sea period show evidence of spatial organization with different organism types clustered in distinct areas according to environmental conditions. Some areas were dominated by large fronds, others by mobile grazers, and still others by diverse assemblages of small, enigmatic forms. One of the most striking features of White Sea ecosystems was their apparent stability. Unlike modern marine communities, which are constantly being disrupted by bioturbation as organisms burrow through the sediment, Ediacaran seafloors remained largely undisturbed. The absence of deep burrowing meant that microbial mats could develop and persist, creating stable habitat structures that supported complex communities for extended periods. This stability had profound implications for ecosystem development. Without constant disturbance, organisms could invest in large, complex body structures that would be vulnerable to destruction in more dynamic environments. The lack of predation pressure also allowed for experimentation with body plans that would later prove untenable once more aggressive feeding strategies evolved. The White Sea period also witnessed important innovations in organism construction and biomineralization. While most Ediacaran organisms remained entirely soft-bodied, some began incorporating rigid elements into their structure. Claudina, discovered in rocks from this period, represents one of the earliest examples of biomineralization, producing calcium carbonate tubes that provided protection and structural support. These early experiments in biomineralization would prove prophetic, presaging the massive expansion of shelled organisms that would characterize the Cambrian explosion. But during the White Sea period, such innovations remained rare, limited to a few pioneering lineages that were testing the boundaries of what was biologically possible. The success of White Sea ecosystems wasn't just measured in terms of diversity and complexity. These communities also achieved remarkable geographic distribution, with similar assemblages found in locations as distant as Russia, Australia, and Namibia. This global distribution indicates that the innovations of the White Sea period weren't local experiments, but represented fundamental breakthroughs in ecosystem organization that could be successfully replicated across a wide range of environmental conditions. As the White Sea period progressed, however, signs of change began to appear. Around 550 million years ago, the stable, mat-dominated ecosystems that had characterized the Ediacaran world began to face new challenges. Environmental conditions were shifting, ocean chemistry was evolving, and new types of organisms were beginning to appear that would fundamentally alter the rules of ecosystem participation. The transition from the White Sea to the final phase of Ediacaran evolution represents one of the most dramatic ecological transformations in Earth's history. The Nama assemblage, named after fossil localities in Namibia, would witness the emergence of new feeding strategies, the breakdown of microbial mat dominance, and the first hints of the predator-prey relationships that would come to define all subsequent ecosystems. But that transformation was still millions of years in the future. For now, in the warm, shallow seas of the White Sea period, Earth's first complex ecosystems thrived in a world unlike anything that would ever exist again. These were the pioneers, the biological innovators who proved that complex life was not only possible but inevitable. Their legacy would echo through the next 500 million years, providing the foundation upon which all subsequent ecosystems would be built. The story of the White Sea assemblage reminds us that evolution is not a linear progression toward greater complexity, but rather an ongoing experiment in the art of living. These ancient organisms, with their alien body plans and mysterious feeding strategies, represent solutions to ecological challenges that we're only beginning to understand. They remind us that life's creativity knows no bounds, and that even in the most ancient chapters of Earth's history, we can find innovations that continue to inspire and amaze us today. The emergence of the Nama assemblage around 550 million years ago marked the beginning of the end for the Ediacaran world as we knew it. Named after the fossil-rich localities in Namibia, where many of these specimens were first discovered, this final phase of Ediacaran evolution witnessed transformations so profound that they would fundamentally reshape the nature of life on Earth. What makes the Nama period so fascinating is that it represents a world in transition. The stable, mat-dominated ecosystems that had persisted for millions of years were beginning to break down, not through some catastrophic event, but through the gradual emergence of new biological innovations that would prove incompatible with the old ways of living. The most dramatic change was the appearance of organisms with hard shells and protective structures. Claudina, a small tube-building creature, became one of the first organisms to construct elaborate calcium carbonate shells. These weren't simple protective coverings, but sophisticated architectural achievements, with nested cone-shaped segments that provided both structural support and defense against environmental hazards. But Claudina wasn't building these shells in isolation. The very fact that such protective structures were evolving suggests that the peaceful world of the White Sea period was giving way to something more dangerous. For the first time in Earth's history, there was evidence of organisms deliberately damaging other organisms. Claudina shells have been found with distinctive boreholes, circular perforations that appear to have been drilled by predators attempting to access the soft tissues inside. These boreholes represent one of the most significant discoveries in all of paleontology. They provide the earliest direct evidence of predator-prey relationships, marking the moment when the arms race between offense and defense began in earnest. The appearance of these interactions wasn't just a biological curiosity. It was a fundamental shift in how ecosystems operated, introducing dynamics of competition and conflict that would drive evolutionary innovation for the next 500 million years. The implications of this shift were staggering. For millions of years, Ediacaran organisms had coexisted in what appears to have been a largely peaceful world. Resources were abundant, competition was limited, and the biggest challenge facing most organisms was simply extracting enough nutrients from their environment to survive and grow. The emergence of predation changed everything, introducing selective pressures that would favor speed, strength, protective structures, and sensory capabilities. Alongside Claudina, other shelled organisms began to appear during the Nama period. Namacalathus, another tube-building creature, developed a different approach to protection, creating goblet-shaped structures with complex internal architecture. These organisms were pioneering new ways of life that required active construction and maintenance of their protective shells. The energy requirements for shell construction were enormous by Ediacaran standards. Unlike the soft-bodied organisms that had dominated earlier periods, these new creatures had to extract calcium and carbonate ions from seawater and organize them into precise crystal structures. This required sophisticated biochemical machinery and represented a major evolutionary investment in defense and structural support. But the changes during the Nama period weren't limited to the evolution of hard shells. The entire structure of seafloor communities was being transformed by the emergence of new feeding strategies and behaviors. For the first time in Earth's history, organisms began to burrow actively into the sediment, disrupting the microbial mats that had provided the foundation for Ediacaran ecosystems. The evidence for this bioturbation revolution is written clearly in the fossil record. Nama-age rocks contain the first abundant trace, fossils, that preserve tracks, trails, and burrows left behind by mobile organisms. These traces tell a story of increasing biological activity and environmental disturbance that stands in stark contrast to the stable mat grounds of earlier periods. Treptichnus pedum, a distinctive branching burrow system, became so characteristic of this transition that it was chosen as the official marker for the end of the Ediacaran period and the beginning of the Cambrian. The appearance of these complex burrow networks indicates that organisms had developed the capability and motivation to actively modify their environment on an unprecedented scale. The ecological consequences of widespread bioturbation were profound. As organisms began to churn through the seafloor sediments, they disrupted the layered structure of microbial mats, mixing oxygen-rich surface layers with deeper anoxic zones. This disruption had cascading effects throughout the ecosystem, altering nutrient cycling, oxygen distribution, and habitat availability. For many traditional Ediacaran organisms, this environmental disruption was catastrophic. The stable mat grounds that had supported large frond-like creatures for millions of years were being systematically destroyed by the activities of a new generation of mobile burrowing organisms. The sessile lifestyle that had worked so well in the peaceful world of the White Sea period became increasingly untenable in the more dynamic environments of the Nama period. Some Ediacaran groups attempted to adapt to these changing conditions. certain frond-like organisms developed stronger attachment structures, anchoring themselves more securely to resist the increasing environmental disturbance. Others evolved more compact body plans that were less vulnerable to damage from mobile neighbours. But these adaptations were largely unsuccessful in the long term. The diversity of the classic Ediacaran biota began to decline during the Nama period, not through mass extinction, but through gradual replacement by organisms better adapted to the new environmental conditions. This transition represents one of the most significant ecological transformations in Earth's history, marking the end of one evolutionary experiment and the beginning of another. Meanwhile, entirely new types of organisms were appearing that would prove more successful in the emerging world of active predation and environmental disturbance. Small shelly fossils, representing various early arthropods, mollusks, and other familiar animal groups, began to appear in the fossil record. These creatures possessed the mobility, sensory capabilities, and defensive structures necessary to thrive in increasingly competitive ecosystems. The appearance of these new organism types during the Nama period provides crucial insights into the relationship between the Ediacaran biota and the animals that would dominate the Cambrian explosion. Rather than representing a complete break with the past, the Nama assemblage shows clear evidence of evolutionary continuity, with some lineages transitioning successfully from the Ediacaran world into the Cambrian. Kimberella, a fascinating organism from the late Ediacaran, represents one of the best examples of this evolutionary transition. This creature possessed a muscular foot similar to that of modern mollusks and appears to have been capable of active locomotion across the seafloor. Fossil trackways associated with Kimberella show evidence of sophisticated feeding behavior, with the organism apparently scraping microbial mats in systematic patterns to maximize nutrient extraction. The feeding traces left by Kimberella reveal a level of behavioral complexity that was unprecedented in earlier Ediacaran organisms. Rather than simply absorbing nutrients passively or grazing randomly across the sea floor, Kimberella appears to have employed deliberate feeding strategies that required planning and spatial awareness. This represents a crucial step toward the more sophisticated behaviors that would characterize Cambrian animals. The success of organisms like Kimberella during the Nama period highlights the importance of active feeding strategies in the changing Ediacaran world. As environmental conditions became more dynamic and competitive, organisms that could actively seek out and exploit food resources had significant advantages over those that relied on passive feeding methods. This shift toward more active lifestyles was accompanied by important innovations in body plan organization. Many Nama period organisms show evidence of bilateral symmetry, concentrated nervous systems, and specialized sensory organs. These features would become characteristic of the bilaterian animals that would dominate the Cambrian explosion and all subsequent ecosystems. The development of bilateral symmetry was particularly significant because it enabled more efficient locomotion and the evolution of directional movement. Unlike the radial symmetry that characterized many earlier Ediacaran organisms, bilateral symmetry allowed for the development of distinct front and rear ends, facilitating the evolution of head regions with concentrated sensory organs and nervous systems. These neurological innovations were crucial for success in the increasingly complex ecosystems of the Nama period. As predator-prey relationships became more common and environmental conditions more variable, organisms needed sophisticated sensory capabilities to detect threats, locate food sources, and navigate their environment effectively. The fossil record from the Nama period also provides evidence for the earliest examples of complex behavioral interactions between different species. Trace fossils show evidence of organisms following each other's tracks, suggesting that some creatures were using chemical or visual cues to locate food sources or mates. This represents a level of ecological sophistication that was entirely absent from earlier Ediacaran ecosystems. The emergence of these complex behaviors was facilitated by improvements in preservation conditions during the Nama period. Unlike the predominantly soft-bodied organisms of earlier periods, many Nama creatures possessed hard shells, or left distinctive trace fossils that were more likely to be preserved in the geological record. This has given paleontologists unprecedented insights into the behavioral ecology of late Ediacaran organisms. One of the most remarkable discoveries from the Nama period is evidence for the earliest known reef-building organisms. Namapoikia, a sponge-like creature, constructed complex three-dimensional structures that provided habitat for diverse communities of smaller organisms. These early reefs represent a crucial innovation in ecosystem engineering, creating new types of habitat structure that would become increasingly important in subsequent periods. The construction of reef-like structures required sophisticated coordination between individual organisms and represented a major advance in biological construction techniques. Unlike the simple tube building of organisms like Cloudina, reef construction involved multiple individuals working together to create complex, three-dimensional habitat structures. These early reefs also provided important refugia for traditional Ediacaran organisms that were struggling to adapt to the changing environmental conditions. Within the protected spaces of reef structures, soft-bodied fronds and other classic Ediacaran forms could persist longer than in the increasingly disturbed open seafloor environments. However, the overall trajectory of change during the Nama period was clear. The peaceful, stable world that had characterized most of the Ediacaran period was giving way to something more dynamic, competitive, and dangerous. The innovations that emerged during this time, particularly predation, bioturbation, and biomineralization, would prove to be game changers that would reshape the fundamental rules of ecosystem participation. The chemical signature of this transformation is preserved in the rocks themselves. Nama period sediments show evidence of increasing bioturbation, with the layered structures characteristic of microbial mats being replaced by the homogenized sediments produced by active burrowing. The carbon isotope signatures also change during this period, reflecting alterations in ocean chemistry and biological productivity associated with the ecological transition. These geochemical changes weren't simply local phenomena, but appear to have been global in scope, indicating that the ecological transformations of the Nama period were occurring simultaneously across multiple continents and ocean basins. This suggests that the driving forces behind these changes were fundamental shifts in environmental conditions rather than isolated evolutionary innovations. As we approach the end of the Ediacaran period, around 541 million years ago, the stage was set for one of the most dramatic evolutionary events in Earth's history. The Cambrian explosion would see the rapid diversification of animal life into most of the major groups that still dominate ecosystems today. But this explosion didn't occur in a vacuum. It was built on the foundation laid during the Ediacaran period, particularly during the transitional Nama phase. The organisms that survived the Ediacaran-Cambrian transition were those that had successfully adapted to the new realities of predation, competition, and environmental disturbance. They possessed the mobility, sensory capabilities, and defensive structures necessary to thrive in the more dynamic ecosystems that were emerging. These survivors would become the ancestors of virtually all modern animal groups. Looking back at the entire sweep of Ediacaran evolution, from the fractal pioneers of the Avalon explosion through the diverse communities of the White Sea period to the transitional ecosystems of the Nama assemblage, we can see a clear progression toward greater complexity, interaction, and ecological sophistication. Each phase built on the innovations of the previous one, creating a cascade of evolutionary advances that ultimately led to the complex ecosystems we know today. The Ediacaran period represents far more than just a prelude to the Cambrian explosion. It was a crucial experimental phase in the evolution of complex life, a time when biology tested the fundamental concepts of multicellularity, ecosystem organization, and ecological interaction. Many of these experiments would prove unsuccessful in the long term, but they provided essential stepping stones toward the more familiar forms of life that would emerge in subsequent periods. Perhaps most importantly, The Ediacaran period demonstrates that evolution is capable of producing solutions to ecological challenges that are completely unlike anything in our modern experience. The rangeomorphs with their fractal architecture, the peaceful communities of the White Sea period, and the strange tube builders of the Nama assemblage remind us that life's creativity knows no bounds. As we stand at the threshold between the Ediacaran world and the explosive diversification of the Cambrian, we can appreciate the magnitude of the transformation that was about to unfold. The foundations had been laid, the basic principles of complex ecosystem organization had been established, and the stage was set for the next great chapter in the story of life on Earth. The final moments of the Ediacaran period weren't marked by catastrophe or sudden collapse. Instead, they unfolded like a slow-motion transformation, a gradual replacement of one world by another. By 541 million years ago, the bizarre experiments in living that had defined the Ediacaran were giving way to something that would prove far more enduring and familiar. But here's what makes this transition so remarkable. The organisms that emerged victorious from this evolutionary contest weren't necessarily the biggest, the most complex, or even the most abundant. They were the ones that had learned to fight back. The trace fossil Treptichnus pedum marks the official boundary between the Ediacaran and Cambrian periods, but it represents so much more than an arbitrary line drawn by geologists. These intricate, branching burrow systems tell the story of organisms that had developed something unprecedented in Earth's history, the ability to actively engineer their environment on a massive scale. Think about what this meant for a moment. For over 30 million years, the seafloor had been dominated by stable microbial mat communities that created predictable, layered environments. Organisms knew where to find oxygen, where to locate nutrients, and where to establish themselves for optimal survival. The world had rules, and those rules had remained consistent for geological ages. The appearance of complex burrowing shattered those rules forever. Suddenly, the seafloor became a three-dimensional battlefield where organisms could tunnel beneath their competitors, disrupt established communities, and create entirely new types of habitat. The stable world of the microbial mats gave way to a dynamic environment where change was the only constant. This bioturbation revolution wasn't just about individual survival strategies. It fundamentally altered the chemistry and physics of marine ecosystems. When organisms began systematically churning through seafloor sediments, they mixed oxygen-rich surface layers with deeper anoxic zones, creating complex gradients of chemical conditions that hadn't existed before. The cascading effects were extraordinary. Nutrient cycling accelerated. Oxygen distribution became more heterogeneous. The predictable layered structure that had supported Ediacaran communities for millions of years dissolved into a churning mixture of chemical microenvironments that favored entirely different types of organisms. For the classic Ediacaran biota, this transformation was devastating. Imagine being a large sessile frond that had spent millions of years perfecting the art of extracting nutrients from stable water columns, only to find your anchoring substrate being constantly disrupted by mobile neighbours. The peaceful coexistence that had characterized the White Sea period became impossible to maintain. Some Ediacaran lineages attempted desperate adaptations. Certain fronds developed more robust attachment structures, anchoring themselves deeper into the sediment. Others evolved more flexible body plans that could bend and sway with increasing environmental turbulence. A few experimented with mobility, attempting to join the ranks of the active organisms that were reshaping their world. But these adaptations were largely unsuccessful. The fundamental architecture of Ediacaran organisms had been optimized for a stable world that no longer existed. Their large surface areas, designed for maximum nutrient absorption, made them vulnerable to damage. Their sessile lifestyles, once an efficient energy conservation strategy, became a fatal liability in increasingly dynamic environments. The decline of the Ediacaran biota wasn't a mass extinction in the traditional sense. There were no asteroid impacts, volcanic catastrophes, or sudden environmental collapses. Instead, it was a gradual ecological replacement, a slow-motion changing of the guard as one evolutionary experiment gave way to another. This process of replacement reveals something profound about how evolution operates over geological timescales. Success isn't always about being the most sophisticated or complex organism in your environment. Sometimes it's about being the most adaptable when the rules of the game suddenly change. The organisms that thrived during this transition possessed characteristics that would seem familiar to anyone studying modern ecosystems. They were mobile, responsive to their environment, capable of complex behaviors, and equipped with sensory systems that allowed them to navigate an increasingly unpredictable world. Cambrian exemplifies this new breed of survivor. This remarkable organism combined the soft-bodied architecture of classic Ediacaran forms with behavioral innovations that would prove crucial for success in the emerging world. Its muscular foot allowed for directed movement across the seafloor, while its systematic feeding patterns revealed a level of behavioral sophistication that was unprecedented in earlier periods. The feeding traces left by Cambrian tell a fascinating story of adaptive intelligence. Rather than randomly grazing across microbial mats like earlier organisms, Cambrian appears to have employed deliberate strategies that maximize nutrient extraction while minimizing energy expenditure. These traces show evidence of systematic scraping patterns, suggesting that the organism could remember where it had fed and avoid depleted areas. This behavioral complexity required neurological innovations that would become characteristic of all subsequent animal evolution. The development of centralized nervous systems, concentrated sensory organs, and the ability to process and respond to environmental information represented a fundamental shift in how organisms interacted with their world. But Cambrian wasn't alone in pioneering these innovations. Across the late Ediacaran world, organisms were experimenting with new approaches to survival that emphasized activity, awareness, and adaptability. The passive, filter-feeding lifestyle that had dominated earlier periods was being supplemented by active predation, directed movement, and complex behavioral interactions. The emergence of predator-prey relationships during this period represents one of the most significant evolutionary innovations in Earth's history. The boreholes found in Cloudina shells provide direct evidence that organisms had begun to view each other not just as competitors for resources, but as resources themselves. This shift toward predation introduced entirely new selective pressures into Ediacaran ecosystems. For the first time in Earth's history, being noticed by another organism could be fatal. This created powerful incentives for the evolution of defensive structures, escape behaviors, and sensory systems capable of detecting approaching threats. The arms race between predator and prey that began during the late Ediacaran would prove to be one of the most important drivers of evolutionary innovation for the next 500 million years. Every improvement in hunting ability would be matched by advances in defensive capabilities, creating a continuous cycle of biological innovation that would push complexity to unprecedented levels. Cloudina's calcium carbonate tubes represent just the beginning of this defensive revolution. These structures required sophisticated biochemical machinery to extract calcium and carbonate ions from seawater and organize them into precise crystal lattices. The energy investment required for shell construction was enormous, but the protection it provided was increasingly essential for survival. The success of shelled organisms during the late Ediacaran demonstrated the viability of biomineralization as a survival strategy. This innovation would explode during the Cambrian period, producing an incredible diversity of shells, spines, plates, and other hard structures that would transform the fossil record and fundamentally alter ecosystem dynamics. But biomineralization wasn't the only defensive innovation emerging during this period. Some organisms experimented with burrowing as a means of escape, creating the complex tunnel systems that would become increasingly common in subsequent periods. Others developed enhanced mobility, using speed and agility to avoid predation. The diversification of defensive strategies during the late Ediacaran created new types of ecological interactions that hadn't existed in earlier periods. Predators had to become more sophisticated to overcome defensive innovations, while prey species had to balance the costs of defense against the benefits of protection. This evolutionary arms race was accompanied by important innovations in body plan organization. The bilateral symmetry that became characteristic of most animal groups provided significant advantages for directed movement and the concentration of sensory organs in head regions. This architectural innovation allowed for more efficient locomotion and the development of sophisticated nervous systems. The concentration of sensory organs in distinct head regions represented a crucial step toward the complex nervous systems that would characterize Cambrian animals. These neurological advances enabled organisms to process environmental information more efficiently and respond more rapidly to changing conditions. The fossil record from the late Ediacaran provides tantalizing glimpses of these neurological innovations. While soft tissues are rarely preserved, the behavioral evidence preserved in trace fossils reveals increasingly sophisticated patterns of movement and feeding that required complex coordination and decision-making abilities. Some of the most remarkable trace fossils from this period show evidence of organisms following each other's trails, suggesting that chemical communication had evolved as a means of locating food sources or potential mates. These early examples of inter-organism communication represent precursors to the complex social behaviors that would emerge in later periods. The development of chemical communication systems required significant advances in both sensory capabilities and signal production. Organisms had to evolve the ability to detect and interpret chemical signals, while also developing mechanisms for producing distinctive chemical signatures. These communication innovations were facilitated by the increasingly complex, three-dimensional structure of late Ediacaran ecosystems. The emergence of reef-building organisms like Nemopoikia created new types of habitat architecture that provided numerous opportunities for chemical signal transmission and reception. Early reef systems also served as crucial refugia during the ecological transition at the end of the Ediacaran. Within the protected spaces of these three-dimensional structures, some traditional Ediacaran organisms could persist longer than in the increasingly disturbed open seafloor environments. The construction of reef-like structures required unprecedented levels of coordination between individual organisms. Unlike the simple tube building of organisms like Claudina, reef construction involved multiple individuals working together to create complex habitat structures that benefited entire communities. This early example of ecosystem engineering demonstrates that late Ediacaran organisms had developed sophisticated mechanisms for environmental modification. The ability to actively construct habitat structures would become increasingly important in subsequent periods, leading to the development of coral reefs, stromatolite buildups, and other biological constructions. The chemical signatures preserved in late Ediacaran rocks reveal the magnitude of the ecological transformation taking place during this period. Carbon isotope ratios shift dramatically, reflecting changes in biological productivity and ocean chemistry associated with the emergence of new ecosystem dynamics. Oxygen isotope data indicates that global climate conditions were also changing during the late Ediacaran, with evidence for cooling temperatures and altered precipitation patterns. These environmental changes may have contributed to the ecological transitions by creating new selective pressures and environmental challenges. The geographic distribution of late Ediacaran fossils reveals that these ecological transformations were occurring simultaneously across multiple continents and ocean basins. This global synchrony suggests that the driving forces behind these changes were fundamental shifts in planetary systems rather than isolated regional phenomena. As we approach the Ediacaran-Cambrian boundary, the pace of change accelerates dramatically. The final few million years of the Ediacaran period witnessed an explosion of innovation in body plans, behaviors, and ecological strategies that would set the stage for the Cambrian radiation. The organisms that successfully navigated this transition possessed a remarkable combination of characteristics that would prove essential for survival in the more complex ecosystems that were emerging. They were mobile enough to escape threats and exploit new opportunities, yet sophisticated enough to construct protective structures and engage in complex behaviors. Most importantly, they had developed the sensory and neurological capabilities necessary to thrive in a world where information processing and rapid decision-making had become matters of life and death. The peaceful, predictable world of the early Ediacaran had given way to something far more dangerous, but also far more dynamic and creative. The legacy of these late Ediacaran pioneers extends far beyond their immediate survival. The innovations they developed, from biomineralization and complex burrowing to predation and chemical communication, would become the foundation stones upon which all subsequent ecosystem evolution would be built. Looking back across the entire span of the Ediacaran period, we can see a clear progression from the simple fractal experiments of the Avalon explosion through the diverse communities of the White Sea period to the transitional ecosystems of the Nama assemblage. Each phase represented a crucial step in the development of complex life, testing different approaches to multicellularity and ecological organization. The Ediacaran world ultimately proved to be a testing ground for biological innovation, a vast laboratory where evolution experimented with different solutions to the challenges of complex life. Many of these experiments would prove unsuccessful in the long term, but they provided essential stepping stones toward the more familiar forms of organization that would emerge during the Cambrian explosion. What makes the Ediacaran story so compelling is its demonstration that evolution is capable of producing solutions that are completely unlike anything in our modern experience. The rangermorphs with their fractal architecture, the peaceful mat-ground communities, and the strange tube builders of the Nama period remind us that life's creativity knows no bounds. As the Ediacaran period drew to a close, the stage was set for one of the most dramatic evolutionary events in Earth's history. The foundations had been laid, the basic principles of complex ecosystem organization had been established, and a new generation of organisms had emerged that possessed the tools necessary to thrive in increasingly competitive and dangerous environments. The Cambrian explosion that would follow wasn't a sudden burst of creativity from nothing. It was the culmination of 90 million years of experimentation, innovation, and ecological development that had begun in the aftermath of Snowball Earth and reached its crescendo in the transitional ecosystems of the late Ediacaran. The organisms that would dominate the Cambrian seas were the direct descendants of the pioneers who had navigated the challenges of the Ediacaran world. They carried within their bodies and behaviors the accumulated wisdom of millions of years of evolutionary experimentation, refined through the crucible of ecological transition. And so, the Ediacaran world passed into history, not with a bang, but with a transformation. The peaceful, alien ecosystems that had flourished for so long gave way to something more familiar, yet infinitely more complex. The age of the rangermorphs was over, but the age of the animals had begun. The story of the Ediacaran period reminds us that evolution is not a linear progression toward predetermined goals, but an ongoing experiment in the art of living. Each period, each ecosystem, each organism represents a unique solution to the challenges of existence, shaped by the specific environmental conditions and evolutionary pressures of its time. In studying these ancient worlds, we gain not just knowledge of the past, but insights into the fundamental processes that continue to shape life on Earth today. The innovations that emerged during the Ediacaran period, from multicellularity and complex ecosystem organization to predation and biomineralization, remain central to understanding how life responds to environmental change and evolutionary challenge. The Ediacaran world may be gone, but its legacy lives on in every ecosystem that has existed since. From the smallest bacterial communities to the most complex marine and terrestrial environments, all carry within them the fundamental organizational principles that were first tested and refined during those crucial 90 million years between snowball Earth and the Cambrian explosion. As we face our own period of rapid environmental change and ecosystem transformation, the lessons of the Ediacaran world become increasingly relevant. They remind us that life is remarkably adaptable and creative, capable of finding solutions to seemingly impossible challenges and thriving under conditions that initially appear hostile to complex organization. The rise of the first ecosystems during the Ediacaran period represents one of the most remarkable achievements in the history of life on Earth. It demonstrates that given sufficient time and opportunity, evolution will inevitably push toward greater complexity, more sophisticated organization, and more intricate ecological relationships. And perhaps most importantly, it shows us that even the most alien and unfamiliar forms of life are connected to us through the deep threads of evolutionary history. The Rangermorphs and Dickinsonia, Cloudina and Kimberella, all these strange and wonderful creatures were our ancestors in the broadest sense, the pioneers who established the basic principles of complex life that we continue to embody today. Their world may have been unlike anything that exists today, but their legacy surrounds us in every breath we take, every step we make, and every moment we spend marveling at the incredible complexity and beauty of the living world they helped to create. The transition into the Cambrian wasn't a sudden switch from one world to another. It was more like watching a slow-motion explosion, where each frame revealed new innovations that would reshape the rules of existence forever. By 541 million years ago, the gentle giants of the Ediacaran were giving way to something far more aggressive, far more complex, and infinitely more familiar. What fascinates me about this transition is how it reveals the true nature of evolutionary change. We often think of evolution as a gradual, steady process, but the end of the Ediacaran shows us something different. Sometimes change accelerates, cascading through ecosystems like dominoes falling in increasingly rapid succession. The final million years of the Ediacaran witnessed an unprecedented explosion of trace fossil diversity. These weren't just random scratches in the sediment. They were signatures of increasingly sophisticated behaviors, evidence of organisms that had learned to navigate their world with purpose and intention. Rusophycus, the resting traces left by early arthropod-like creatures, tells us that organisms had developed the ability to pause, assess their environment, and make deliberate decisions about where to position themselves for optimal survival. These trace fossils reveal creatures that could evaluate substrate quality, assess predation risk, and choose their locations based on complex environmental calculations. The appearance of Cruziana traces adds another layer to this story. These distinctive trackways, created by organisms moving systematically across the seafloor, demonstrate that late Ediacaran creatures had developed sophisticated locomotion strategies. The regular parallel scratches left by these organisms suggest the presence of jointed appendages and coordinated movement patterns that would become characteristic of arthropod groups. But perhaps most telling are the skelethos traces, vertical burrows that penetrate deep into the sediment. These structures represent a complete revolution in how organisms interacted with their substrate. Rather than simply resting on top of microbial mats or burrowing shallow feeding traces, these creatures were actively colonizing the three-dimensional space beneath the seafloor. The construction of vertical burrows required remarkable physiological adaptations. Organisms had to develop mechanisms for maintaining oxygen supply in confined spaces, dealing with increased pressure at depth, and managing waste products in enclosed environments. These challenges pushed the evolution of circulatory systems, respiratory structures, and metabolic pathways that would prove crucial for future animal success. The energy investment required for deep burrowing was enormous, but the benefits were equally significant. Vertical burrows provided protection from surface predators, access to buried food resources, and stable environmental conditions that buffered organisms against surface fluctuations. This three-dimensional colonization of the seafloor represented a massive expansion of available habitat space. As more organisms adopted burrowing lifestyles, the character of seafloor environments changed dramatically. The stable, layered structure of microbial mat communities gave way to intensely bioturbated sediments, where constant churning created a dynamic mosaic of chemical and physical conditions. This bioturbation had cascading effects throughout the ecosystem. Oxygen penetration increased as burrow networks created conduits for water circulation. Nutrient cycling accelerated as organisms transported materials between different sediment layers. The predictable chemical gradients that had characterized Ediacaran seafloors were replaced by complex, shifting patterns that favored organisms with greater physiological flexibility. For the remaining Ediacaran organisms, these changes represented an existential crisis. The environmental stability that had allowed them to thrive for millions of years was being systematically destroyed by the activities of their more active neighbors. Large fronds found their attachment sites constantly disrupted. Sessile filter feeders discovered that their carefully positioned feeding structures were being buried or damaged by passing burrowers. Some lineages attempted last-ditch adaptations to survive in the changing world. Certain frondose organisms developed more robust support structures, creating thicker stems and more extensive root systems to anchor themselves in increasingly unstable substrates. Others experimented with smaller body sizes, reducing their vulnerability to environmental disturbance. A few groups tried to join the mobility revolution, developing primitive locomotion capabilities that allowed them to relocate when conditions became unfavorable. But these adaptations were largely unsuccessful. The fundamental architecture of Ediacaran organisms had been optimized for a world that no longer existed. The decline of classic Ediacaran forms wasn't uniform across all environments. In some protected settings, particularly within reef structures and other three-dimensional habitats, traditional organisms managed to persist longer than in open seafloor communities. These refugia provided glimpses of what Ediacaran ecosystems had been like during their heyday. But even in these protected environments, change was inevitable. The organisms that had learned to burrow, hunt, and compete were gradually expanding into every available niche. Their superior mobility, sensory capabilities, and behavioral flexibility gave them decisive advantages in resource competition. The geochemical signature of this transition is preserved in extraordinary detail in rocks from around the world. Carbon isotope ratios shift dramatically across the Ediacaran Cambrian boundary, reflecting fundamental changes in biological productivity and ecosystem metabolism. The stable isotope patterns that had characterized the Ediacaran world gave way to more variable signatures that reflected the increased complexity of biological processes. Phosphorus availability also changed during this period, with evidence for increased nutrient cycling associated with bioturbation activities. The enhanced mixing of seafloor sediments brought buried nutrients back into circulation, potentially fueling the biological innovations that were transforming marine ecosystems. Trace element compositions in late Ediacaran rocks revealed changing ocean chemistry conditions that may have influenced the evolutionary transitions taking place. Molybdenum and uranium concentrations indicate fluctuating oxygen levels that created selective pressures for organisms with more sophisticated respiratory systems. The global nature of these geochemical changes suggests that the ecological transformation at the end of the Ediacaran was driven by planetary-scale processes rather than isolated regional phenomena. Climate data indicates that Earth was experiencing significant environmental changes during this period, with evidence for cooling temperatures and altered ocean circulation patterns. These environmental changes may have created the selective pressures that favored more active, mobile organisms over the sessile forms that had dominated earlier periods. Organisms with greater behavioral flexibility would have been better able to track favorable conditions and avoid environmental hazards. The fossil record from the latest Ediacaran provides tantalizing glimpses of the organisms that would dominate the Cambrian explosion. Small shelly fossils begin to appear with increasing frequency, representing early experiments in biomineralization that would expand dramatically in subsequent periods. Anaborites, Protohertzina, and other tiny shelled organisms demonstrate that the basic biochemical machinery for constructing hard parts had evolved by the end of the Ediacaran. These early shells were simple compared to later Cambrian examples, but they established the fundamental principles of biomineralization that would prove so important for future evolution. The appearance of small shelly fossils also indicates that organism size was changing during the transition period. While classic Ediacaran forms had often been quite large, many of the successful transitional organisms were much smaller. This size reduction may have been an adaptation to the increasingly competitive and dangerous conditions of late Ediacaran ecosystems. Smaller organisms could reproduce more rapidly, exploit resources more efficiently, and avoid predation more successfully than their larger competitors. This trend toward miniaturization would be temporarily reversed during the Cambrian explosion, but it established important principles about the relationship between body size and ecological success. The diversification of feeding strategies during the latest Ediacaran was truly remarkable. While early periods had been dominated by osmotrophic and suspension feeding, the final phase witnessed the emergence of deposit feeding, grazing, predation, and scavenging. This explosion of trophic diversity created complex food webs that bore little resemblance to the simple communities of earlier periods. Deposit feeding, in particular, became increasingly important as bioturbation activities made buried organic matter more accessible. Organisms evolved specialized structures for processing sediment and extracting nutrients from organic particles. These feeding innovations required sophisticated digestive systems and represented major advances in physiological complexity. The emergence of active predation introduced entirely new dynamics into ecosystem functioning. For the first time in Earth's history, energy could flow efficiently from one trophic level to another through direct consumption rather than decomposition. This created opportunities for the evolution of larger, more complex organisms that could exploit the energy stored in other living creatures. Scavenging also became an important feeding strategy as predation and natural mortality created a steady supply of dead organic matter. Organisms evolved sensory capabilities for locating carrion and behavioral strategies for accessing and processing dead tissues. This ecological role would become increasingly important in subsequent periods. The development of complex food webs during the latest Ediacaran required sophisticated mechanisms for energy transfer and nutrient cycling. Organisms had to evolve more efficient digestive systems, improved metabolic pathways, and enhanced physiological integration to function effectively in these new ecological contexts. Sensory evolution accelerated dramatically during this period, driven by the need to navigate increasingly complex and dangerous environments. The development of photoreceptive organs allowed organisms to detect shadows, movement, and changes in light intensity that might signal approaching predators or prey. Chemical sensory systems became more sophisticated, enabling organisms to detect and interpret the complex mixture of chemical signals present in bioturbated environments. The ability to distinguish between food odors, predator pheromones, and mate attractants required significant advances in neurological processing capabilities. Mechanical sensory systems also evolved to detect vibrations, pressure changes, and physical contact. These capabilities were essential for organisms living in burrow systems where visual information was limited and chemical signals might be diluted or confused. The integration of multiple sensory modalities required the evolution of centralized nervous systems capable of processing and integrating information from different sources. This neurological complexity would become a defining characteristic of most animal groups and represented one of the most important innovations of the late Ediacaran period. behavioral complexity increased in parallel with sensory sophistication. Organisms developed more elaborate movement patterns, sophisticated feeding strategies, and complex responses to environmental stimuli. The trace fossil record reveals evidence for learning, memory, and even primitive forms of social interaction. Some of the most remarkable trace fossils from this period show evidence of organisms modifying their behavior based on previous experience. Burrow systems become more efficient over time. Feeding traces show evidence of optimization, and movement patterns suggest that organisms could remember and return to productive locations. These behavioral innovations required significant advances in information storage and retrieval systems within the nervous system. The ability to learn from experience and modify behavior accordingly represented a crucial step toward the complex cognitive capabilities that would emerge in later periods. Communication systems also became more sophisticated during the latest Ediacaran. Chemical signaling evolved beyond simple pheromone release to include complex molecular messages that could convey detailed information about identity, reproductive status, and territorial boundaries. Some organisms developed mechanical communication systems, using vibrations or water currents to transmit information to conspecifics. These early examples of acoustic communication would eventually evolve into the complex sound-based communication systems used by many modern animal groups. The evolution of communication required not just the ability to produce signals, but also the capacity to receive, interpret, and respond to messages from other organisms. This created feedback loops that drove the evolution of increasingly sophisticated signaling systems and neurological processing capabilities. Social interactions became more complex as organisms developed the ability to recognize and remember individuals, form temporary associations for mutual benefit, and engage in competitive displays that could resolve conflicts without direct physical confrontation. These social innovations were facilitated by the increasingly three-dimensional nature of late Ediacaran habitats. Burrow systems, reef structures, and other biological constructions created opportunities for organisms to interact in ways that hadn't been possible in the flat mat-ground communities of earlier periods. The construction of complex, three-dimensional habitats represented a form of ecosystem engineering that would become increasingly important in subsequent periods. Organisms that could actively modify their environment gained significant advantages in resource competition and predator avoidance. Some of the most sophisticated habitat construction during the latest Ediacaran involved the creation of tube networks and burrow systems that provided protection for entire communities of organisms. These structures required coordination between multiple individuals and represented early examples of cooperative behavior. The energy investment required for habitat construction was substantial, but the benefits included enhanced protection, improved resource access, and more stable environmental conditions. These advantages helped drive the evolution of increasingly elaborate construction behaviors and architectural innovations. Biomineralization technology advanced rapidly during the final phases of the Ediacaran, with organisms experimenting with different mineral compositions, crystal structures, and construction techniques. The diversity of shell types and skeletal elements that appeared during this period laid the foundation for the explosive radiation of shelled organisms during the Cambrian. Calcium carbonate remained the most common biomineralization material, but organisms also began experimenting with silica, calcium phosphate, and other mineral compositions. Each material had different mechanical properties and required different biochemical pathways for construction. The evolution of biomineralization required sophisticated mechanisms for controlling crystal nucleation, growth, and organization. Organisms had to develop specialized cells for mineral extraction and deposition, as well as organic frameworks for guiding crystal formation. These biomineralization innovations weren't just about protection. Hard parts also provided structural support that enabled the construction of larger, more complex body plans. The ability to build internal and external skeletons opened up entirely new possibilities for organism design and function. Reproductive strategies also underwent significant innovation during the latest Ediacaran. The evolution of sexual reproduction, complex life cycles, and sophisticated developmental programs allowed organisms to adapt more rapidly to changing environmental conditions. The development of planktonic larval stages provided organisms with enhanced dispersal capabilities and allowed them to exploit different environments during different phases of their life cycles. This reproductive flexibility would prove crucial for success in the increasingly variable conditions of the transitional period. Parental care behaviors began to emerge as organisms invested more energy in fewer offspring with higher survival probabilities. These strategies required sophisticated behavioral programs and represented important steps toward the complex reproductive behaviors that would characterize later animal groups. The evolution of complex developmental programs allowed organisms to construct increasingly sophisticated body plans with specialized organ systems, hierarchical organization, and precise anatomical integration. These developmental innovations would prove essential for the construction of the complex body plans that would emerge during the Cambrian explosion. Physiological integration reached new levels of sophistication during the latest Ediacaran, as organisms evolved more efficient circulatory systems, enhanced respiratory structures, and improved metabolic coordination. These advances enabled the construction and maintenance of larger, more active body plans. The development of centralized circulatory systems allowed for more efficient transport of nutrients, gases, and waste products throughout the organism. This physiological innovation was essential for supporting the increased metabolic demands of active lifestyles and complex behaviors. Respiratory efficiency improved through the evolution of specialized gas exchange surfaces, enhanced ventilation mechanisms, and more sophisticated oxygen transport systems. These advances enabled organisms to maintain higher activity levels and support more complex physiological processes. Metabolic coordination became more sophisticated as organisms evolved better mechanisms for regulating energy production, storage, and utilization. The ability to coordinate metabolic processes across different organ systems was essential for maintaining physiological homeostasis in variable environments. Waste management systems also became more efficient as organisms evolved specialized excretory structures and improved mechanisms for maintaining internal chemical balance. These physiological advances were crucial for supporting the increased metabolic complexity of late Ediacaran organisms. The immune system innovations that emerged during this period provided organisms with enhanced capabilities for recognizing and responding to pathogens, parasites, and other biological threats. These defenses became increasingly important as organism density and interaction rates increased. Temperature regulation mechanisms evolved to help organisms maintain optimal physiological function across a wider range of environmental conditions. These adaptations were particularly important as climate conditions became more variable during the latest Ediacaran. Water and ion balance regulation became more sophisticated as organisms evolved better mechanisms for maintaining internal osmotic conditions. These physiological capabilities were essential for organisms living in the chemically complex environments created by bioturbation activities. pH regulation systems evolved to help organisms maintain internal chemical balance despite external environmental fluctuations. These buffering mechanisms became increasingly important as ocean chemistry became more variable during the transition period. The coordination of all these physiological systems required increasingly sophisticated control mechanisms and information processing capabilities. The evolution of complex physiological integration would prove essential for the construction of the large, active organisms that would dominate the Cambrian explosion. As the final moments of the Ediacaran period approached, all these innovations were converging to create something unprecedented in Earth's history. The stage was set for an evolutionary explosion that would dwarf even the remarkable diversification that had characterized the Ediacaran world. The organisms that had successfully navigated the challenges of the transitional period possessed a remarkable toolkit of capabilities that would prove essential for success in the new world that was emerging. They had mobility, sensory sophistication, behavioral complexity, physiological integration, and the ability to construct and maintain complex body plans. Most importantly, they had learned to fight, to compete, and to exploit the opportunities created by conflict and competition. The peaceful world of the early Ediacaran had given way to something far more dynamic and dangerous, but also infinitely more creative and innovative. The innovations that emerged during the final phases of the Ediacaran period would provide the foundation for virtually every major advance in animal evolution over the subsequent 540 million years. From the basic principles of biomineralization to the fundamental architecture of complex nervous systems, the late Ediacaran pioneers established the technological and organizational framework that would support all future evolutionary innovation. And so the Ediacaran world prepared for its final transformation, not knowing that it was about to witness one of the most spectacular explosions of biological creativity in the history of life on Earth. The Cambrian was coming, and it would change everything. Everything. The Ediacaran-Cambrian boundary represents more than just a line on a geological timeline. It marks the moment when Earth's biological experiment shifted into an entirely different gear. By 541 million years ago, the trace fossil Treptychnos pedum had become so abundant in marine sediments that geologists use it as the official marker for the beginning of the Cambrian period. But this wasn't just bureaucratic convenience. These complex, branching burrow systems tell the story of organisms that had fundamentally reimagined what it meant to be alive. Picture this for a moment. An organism encounters the sea floor and doesn't simply rest on its surface or dig a simple vertical shaft. Instead, it constructs an elaborate three-dimensional maze of interconnected tunnels complete with specialized chambers for different activities. Some sections serve as feeding areas, where the creature processes sediment for organic particles. Others function as resting chambers, where it can retreat from danger. Still others appear to be nursery areas where offspring develop in protected environments. The construction of such complex burrow systems required unprecedented levels of behavioral sophistication. These weren't random excavations, but carefully planned architectural projects that demanded spatial awareness, memory, and the ability to coordinate different activities across multiple locations. The organisms responsible for Treptychnos pedum had essentially invented underground cities, but here's what makes this even more remarkable. These burrow systems weren't built by solitary individuals working in isolation. Fossil evidence suggests that multiple organisms often shared and modified the same tunnel networks, creating collaborative construction projects that spanned generations. This represents some of the earliest evidence for complex social behaviors in the animal kingdom. The physiological demands of this burrowing lifestyle were extraordinary. Organisms had to maintain oxygen supplies in confined spaces where water circulation was limited. They needed to manage waste products in enclosed environments. They had to coordinate the movement of materials between different parts of their burrow systems. All of this required circulatory systems, respiratory structures, and metabolic pathways that were orders of magnitude more sophisticated than anything that had existed during the early Ediacaran. The success of these burrowing organisms created a cascade of environmental changes that reverberated throughout marine ecosystems. As more creatures adopted subterranean lifestyles, the character of seafloor environments was transformed beyond recognition. The stable, layered microbial mat communities that had dominated for millions of years gave way to intensely churned sediments, where constant biological activity created a dynamic three-dimensional habitat. This bioturbation revolution had consequences that extended far beyond the immediate vicinity of individual burrows. Oxygen penetration into seafloor sediments increased dramatically as tunnel networks created extensive conduits for water circulation. Nutrients that had been locked away in deep sediment layers were brought back to the surface through the activities of burrowing organisms. The predictable chemical gradients that had characterized Ediacaran sea floors were replaced by complex, shifting mosaics of conditions that changed constantly. For the surviving Ediacaran organisms, this transformation represented an environmental catastrophe of unprecedented proportions. The stable world they had evolved to exploit was being systematically dismantled by creatures that viewed the seafloor not as a surface to rest upon, but as a three-dimensional resource to be exploited. Large frondose organisms found their attachment sites constantly disrupted by passing burrowers. Sessile filter feeders discovered that their carefully positioned feeding structures were being buried under sediment brought up from deeper layers. The gentle water currents that had once delivered nutrients to stationary organisms were now turbulent and unpredictable, carrying suspended particles that could clog delicate feeding mechanisms. Some Ediacaran lineages mounted desperate attempts at adaptation. Certain fronds developed more extensive root systems, spreading their anchor points across wider areas to better resist disturbance. Others experimented with flexible stems that could bend with turbulent water flows rather than breaking under stress. A few groups even attempted to develop mobility, creating primitive muscular systems that allowed limited movement across the seafloor. But these adaptations were largely futile. The fundamental architecture of Ediacaran organisms had been optimized for a world of stability and predictability that no longer existed. Their large surface areas, designed for maximum nutrient absorption from clear water, made them vulnerable to damage from suspended particles. Their sessile lifestyles, once an efficient strategy for energy conservation, became fatal liabilities in environments where the ability to relocate quickly could mean the difference between survival and extinction. The decline of the classic Ediacaran biota wasn't uniform across all environments or all taxonomic groups. In some protected settings, particularly within the complex three-dimensional structures created by reef-building organisms, traditional forms managed to persist longer than in open seafloor communities. These biological refugia provided glimpses of what Ediacaran ecosystems had been like during their peak diversity. Namapoikia reefs, constructed by sponge-like organisms during the later Ediacaran, created islands of stability in an increasingly chaotic world. Within the protected spaces of these reef structures, frondose organisms could anchor themselves securely and filter feed without constant disruption. Small pools and channels within the reef framework provided calm water environments where delicate organisms could continue their ancient lifestyles. But even these refugia were temporary sanctuaries. The organisms that had learned to burrow, hunt, and compete were gradually expanding into every available niche. Their superior mobility, enhanced sensory capabilities, and behavioral flexibility gave them decisive advantages in resource competition. It was only a matter of time before they would colonize even the most protected environments. The geochemical signature of this great transition is preserved with extraordinary clarity in rock formations around the world. Carbon isotope ratios undergo dramatic shifts across the Ediacaran-Cambrian boundary, reflecting fundamental changes in how marine ecosystems processed organic matter. The stable patterns that had characterized the Ediacaran world gave way to much more variable signatures that reflected the increased complexity and dynamism of biological processes. Sulfur isotope compositions also changed significantly during this period, indicating alterations in the cycling of this crucial element through marine ecosystems. The enhanced mixing of seafloor sediments brought sulfur-bearing minerals into contact with oxygenated waters, creating new chemical reactions and altering the availability of sulfur for biological processes. Strontium isotope ratios reveal changes in weathering patterns and continental erosion rates that may have been influenced by the emergence of more complex biological activity. The increased bioturbation of seafloor sediments may have enhanced the efficiency of chemical weathering processes, altering the flux of nutrients from continents to oceans. Phosphorus concentrations in marine sediments increased dramatically during the latest Ediacaran, reflecting the enhanced nutrient cycling associated with bioturbation activities. The systematic churning of seafloor sediments by burrowing organisms brought buried phosphorus-bearing minerals back into circulation, potentially fueling the biological innovations that were transforming marine ecosystems. Trace element compositions provide additional evidence for changing environmental conditions during this crucial transition. Molybdenum and uranium concentrations fluctuate in ways that indicate varying oxygen levels in different parts of the ocean. These chemical signatures suggest that the oxygenation of marine environments was not a simple, uniform process, but involved complex spatial and temporal patterns that created diverse, selective pressures for evolving organisms. The global nature of these geochemical changes indicates that the ecological transformation at the end of the Ediacaran was driven by planetary scale processes rather than isolated regional phenomena. Climate data from this period reveals evidence for significant environmental changes, including cooling temperatures, altered precipitation patterns, and modifications in ocean circulation systems. These environmental changes created selective pressures that favored organisms with greater physiological flexibility and behavioral adaptability, creatures that could actively seek out favorable conditions and avoid environmental hazards had significant advantages over those that remained dependent on passive strategies for dealing with environmental variation. The fossil record from the latest Ediacaran provides increasingly abundant evidence for the organisms that would dominate the coming Cambrian explosion. Small shelly fossils appear with growing frequency, representing early experiments in biomineralization that would expand dramatically in subsequent periods. These tiny structures, often only a few millimeters in length, demonstrate that the basic biochemical machinery for constructing hard parts had evolved by the end of the Ediacaran. Anaborites, with its distinctive tube-like shells marked by longitudinal ribs, represents one of the most successful early biomineralizing organisms. These creatures constructed calcium carbonate tubes that provided protection while allowing them to extend soft feeding structures into the water column. The success of anaborites demonstrated the viability of combining mobility with protective shell construction. Protohertzina developed a different approach to biomineralization, creating small conical shells that could be secreted rapidly and discarded when damaged. This strategy allowed for quick, protective responses to immediate threats while maintaining the flexibility to modify shell design as conditions changed. Claudina, which had appeared earlier in the Ediacaran, continued to diversify during this transition period. Some species developed more elaborate shell architectures with complex folding patterns that provided enhanced protection while maintaining structural efficiency. Others experimented with colonial growth forms that created reef-like structures from aggregations of individual tubes. The appearance and diversification of these small shelly fossils indicates that organism size distributions were changing during the transition period. While classic Ediacaran forms had often been quite large, many of the successful transitional organisms were much smaller. This size reduction may have been an adaptation to the increasingly competitive and dangerous conditions of late Ediacaran ecosystems. Smaller organisms could reproduce more rapidly, allowing populations to recover quickly from environmental disturbances or predation pressure. They could also exploit resources more efficiently, accessing food sources in confined spaces and processing smaller particles that might be overlooked by larger competitors. Perhaps most importantly, small size provided better opportunities for avoiding predation through hiding, rapid escape, or simply being too small to be worth the energy expenditure required to capture and consume them. This trend toward miniaturization would be temporarily reversed during the Cambrian explosion as organisms evolved more sophisticated predator avoidance strategies and more efficient resource exploitation methods. But the late Ediacaran experiments with small body size established important principles about the relationship between organism dimensions and ecological success, that would influence evolutionary patterns for millions of years to come. The diversification of feeding strategies during the latest Ediacaran was truly extraordinary. While earlier periods had been dominated by osmotrophic feeding and simple suspension feeding, the final phase witnessed an explosion of trophic innovations that created complex food webs bearing little resemblance to the simple communities of earlier times. Deposit feeding became increasingly sophisticated as organisms evolved specialized structures for processing sediment and extracting organic particles. These feeding innovations required complex digestive systems capable of breaking down a wide variety of organic compounds and separating useful materials from inorganic sediment particles. The development of such digestive capabilities represented major advances in physiological complexity that would prove essential for success in bioturbated environments. Some deposit feeders developed the ability to selectively target sediment layers with higher organic content, using chemical or mechanical sensors to identify the most nutritious feeding opportunities. Others evolved mechanisms for processing large volumes of sediment quickly, compensating for low nutrient concentrations through high throughput rates. Grazing strategies became more sophisticated as organisms developed better methods for harvesting microbial mat communities. Rather than simply scraping surface materials, some grazers evolved the ability to stimulate microbial growth through their feeding activities, essentially farming the organisms they consumed. This created sustainable feeding relationships that could persist over extended periods. The emergence of active predation introduced entirely new dynamics into ecosystem functioning that had never existed before in Earth's history. For the first time, energy could flow efficiently from one trophic level to another through direct consumption rather than decomposition. This created opportunities for the evolution of larger, more complex organisms that could exploit the concentrated energy stores present in other living creatures. Early predatory strategies were relatively simple, involving the physical overpowering of prey organisms or the exploitation of already weakened individuals. But even these basic predatory behaviors required significant advances in sensory capabilities, locomotion systems, and behavioral coordination that pushed the evolution of nervous system complexity. Some predators specialized in exploiting particular types of prey, developing feeding structures and hunting behaviors optimized for specific targets. Others adopted more generalized strategies, maintaining the flexibility to exploit whatever prey opportunities became available. Both approaches proved successful under different environmental conditions. Scavenging emerged as an important ecological role, as increased mortality from predation and environmental stress created a steady supply of dead organic matter. Organisms evolved enhanced chemosensory capabilities for locating carrion and behavioral strategies for accessing and processing dead tissues before competing scavengers could claim the resources. The development of scavenging behaviors required sophisticated mechanisms for distinguishing between different types of organic matter and assessing the quality and safety of potential food sources. Scavengers had to avoid consuming materials that might be toxic or infected with pathogens while maximizing their exploitation of nutritious resources. Filter feeding strategies became more sophisticated as organisms evolved better mechanisms for capturing and processing suspended particles from the water column. The increasing bioturbation of seafloor environments created higher concentrations of suspended organic matter, providing enhanced opportunities for filter feeding organisms. Some filter feeders developed active pumping mechanisms that could generate strong water currents for capturing particles. Others evolved passive feeding structures that could efficiently extract nutrients from natural water flows. Both strategies required sophisticated anatomical modifications and physiological coordination. The evolution of complex food webs during the latest Ediacaran required unprecedented levels of energy transfer efficiency and nutrient cycling coordination. Organisms had to develop more efficient digestive systems, improved metabolic pathways, and enhanced physiological integration to function effectively in these new ecological contexts. Digestive efficiency improvements included the evolution of specialized enzyme systems for breaking down different types of organic compounds, enhanced absorption mechanisms for extracting nutrients from processed materials, and better waste management systems for eliminating indigestible components. Metabolic pathway optimization allowed organisms to extract more energy from available food sources and convert nutrients more efficiently into growth and reproduction. These physiological advances were essential for supporting the increased energy demands of active lifestyles and complex behaviors. Physiological integration reached new levels of sophistication as organisms evolved better coordination between different organ systems. Improved circulatory systems ensured efficient distribution of nutrients and removal of waste products. Enhanced nervous systems provided better coordination of complex behaviors and rapid responses to environmental stimuli. Sensory evolution accelerated dramatically during this period as organisms faced the challenge of navigating increasingly complex and dangerous environments. The development of sophisticated photoreceptive organs allowed creatures to detect subtle changes in light intensity that might signal approaching predators or prey. These visual systems evolved from simple light-sensitive spots to complex image-forming structures capable of detecting movement, shapes, and even colors. Chemical sensory systems underwent remarkable diversification as organisms developed the ability to detect and interpret an enormous variety of chemical signals. The bioturbated environments of the late Ediacaran contained complex mixtures of chemical compounds from different sources, requiring sophisticated molecular recognition capabilities to distinguish between food odors, predator pheromones, territorial markers, and reproductive signals. Mechanosensory capabilities evolved to detect vibrations, pressure changes, and physical contact with increasing precision. These abilities were particularly important for organisms living in burrow systems where visual information was limited and chemical signals might be diluted or confused by water circulation patterns. The integration of multiple sensory modalities required the evolution of centralized nervous systems capable of processing and combining information from different sources. This neurological complexity enabled organisms to create comprehensive environmental assessments and make sophisticated behavioral decisions based on multiple types of information. Behavioral sophistication increased in parallel with sensory capabilities as organisms developed more elaborate movement patterns, complex feeding strategies, and sophisticated responses to environmental stimuli. The trace fossil record from this period reveals evidence for learning, memory formation, and even primitive forms of social interaction. Some of the most remarkable behavioral innovations involved the development of conditional strategies, where organisms could modify their responses based on environmental context. Feeding behaviors became more flexible, allowing creatures to adjust their techniques based on prey availability and competition intensity. Locomotion patterns became more sophisticated, with organisms developing the ability to navigate complex three-dimensional environments and remember productive routes. Territory establishment and defense behaviors emerged as resources became more limited and competition intensified. Some organisms developed the ability to recognize and maintain territorial boundaries, using chemical marking, physical displays, or aggressive behaviors to exclude competitors from valuable resources. Communication systems evolved beyond simple chemical signaling to include complex behavioral displays and mechanical signal production. Some organisms developed the ability to generate vibrations or water movements that could convey information about identity, reproductive status, or territorial claims to other individuals. The evolution of communication required not just signal production capabilities, but also sophisticated reception and interpretation systems. Organisms had to develop the neurological machinery necessary to distinguish between different types of signals and respond appropriately to the information being conveyed. Social behaviors became more complex as organisms developed enhanced abilities to recognize individuals, form temporary associations for mutual benefit, and engage in coordinated group activities. These early forms of sociality laid the groundwork for the more elaborate social systems that would evolve in later periods. Reproductive strategies underwent significant innovation during the latest Ediacaran, as organisms evolved more sophisticated mechanisms for finding mates, ensuring successful fertilization, and protecting developing offspring. The evolution of sexual reproduction allowed for increased genetic recombination and faster adaptation to changing environmental conditions. Complex life cycles emerged that took advantage of different environmental conditions during different developmental stages. Some organisms evolved planktonic larval phases that provided enhanced dispersal capabilities and allowed exploitation of different food sources during development. Others developed direct development strategies that eliminated vulnerable larval stages but required greater parental investment. Parental care behaviors began to evolve as organisms invested more energy in fewer offspring with higher individual survival probabilities. These strategies required sophisticated behavioral programs and represented important steps toward the complex reproductive behaviors that would characterize later animal groups. The development of sophisticated courtship behaviors allowed organisms to assess potential mate quality and ensure successful reproduction. These behavioral innovations required enhanced sensory capabilities and complex neurological processing systems that could evaluate multiple criteria for mate selection. Developmental complexity increased dramatically as organisms evolved more sophisticated mechanisms for constructing complex body plans during growth. The evolution of precise gene regulation systems allowed for the development of specialized tissues and organ systems with hierarchical organization and functional integration. Pattern formation mechanisms became more sophisticated, enabling the construction of complex anatomical structures with precise spatial organization. These developmental innovations were essential for building the elaborate body plans that would emerge during the Cambrian explosion. Cell differentiation processes evolved to create specialized cell types with distinct functions and properties. This cellular specialization allowed for the evolution of complex organ systems with enhanced performance capabilities and functional efficiency. Tissue organization became more sophisticated as organisms developed better mechanisms for coordinating the activities of different cell types and maintaining proper anatomical relationships during growth and development. The physiological integration that emerged during the latest Ediacaran represented a quantum leap in biological complexity. Organisms evolved more efficient circulatory systems that could maintain precise control over internal transport processes. These systems included specialized pumping mechanisms, branch distribution networks, and sophisticated regulatory controls that could adjust circulation patterns based on changing physiological demands. Respiratory systems became more sophisticated with the evolution of specialized gas exchange surfaces, enhanced ventilation mechanisms, and improved oxygen transport capabilities. These advances enabled organisms to maintain higher metabolic rates and support more active lifestyles than had been possible during earlier periods. Excretory systems evolved to handle the increased waste production associated with more complex metabolic processes. Specialized filtration mechanisms, concentration systems, and elimination pathways allowed organisms to maintain proper internal chemical balance despite higher levels of metabolic activity. Nervous system complexity reached unprecedented levels as organisms evolved centralized processing centers, specialized sensory pathways, and sophisticated motor control systems. These neurological advances enabled the coordination of complex behaviors and rapid responses to environmental challenges. Immune system innovations provided organisms with enhanced capabilities for recognizing and eliminating pathogens, parasites, and other biological threats. These defensive systems became increasingly important as population densities increased and contact rates between different organisms intensified. Homeostatic mechanisms evolved to maintain stable internal conditions despite fluctuating external environments. Temperature regulation, pH control, osmotic balance, and other physiological parameters came under increasingly sophisticated regulatory control that allowed organisms to function effectively across wider ranges of environmental conditions. As these remarkable innovations accumulated during the final phases of the Ediacaran period, they created the foundation for evolutionary possibilities that would have been unimaginable during earlier phases of Earth's history. The organisms that emerged from this crucible of innovation possessed capabilities that would prove essential for success in the new world that was rapidly approaching. The stage was set for the Cambrian explosion, but it wasn't an explosion from nothing. It was the culmination of nearly 100 million years of evolutionary experimentation, innovation, and ecological development that had begun in the aftermath of Snowball Earth and reached its crescendo in the transitional ecosystems of the late Ediacaran. The peaceful world of the Rangermorphs was gone forever, replaced by something far more dynamic, competitive, and creative. The organisms that would inherit the Earth had learned not just to survive, but to thrive through conflict, competition, and constant innovation. They had developed the tools, both biological and behavioral, that would allow them to construct the complex ecosystems that would dominate the next 500 million years of Earth's history. And in those final moments before the Cambrian dawn, as the last Ediacaran communities gave way to something entirely new, our planet prepared for its next great experiment in the endless creativity of life. The age of the animals was about to begin, built upon the remarkable foundation established by the pioneers of the Ediacaran world. The final curtain call of the Ediacaran world wasn't marked by catastrophe or sudden collapse. Instead, it unfolded like a slow-motion metamorphosis, where each passing millennium revealed new players taking center stage, while the old guard gradually faded into the wings of evolutionary history. By 541 million years ago, the very DNA of marine ecosystems was being rewritten by organisms that had mastered arts their predecessors could never have imagined. What strikes me most about this transition is how it reveals the relentless creativity of evolution when faced with environmental pressure. The organisms emerging during these final Ediacaran moments weren't just surviving, they were innovating at a pace that would make modern Silicon Valley entrepreneurs weep with envy. Every challenge became an opportunity for biological breakthrough. Every environmental shift a catalyst for unprecedented adaptation. The trace fossil record from this period reads like a manual for ecosystem revolution. Didymalagnus, with its paired scratch marks, tells us that organisms had evolved paired appendages capable of coordinated movement across the seafloor. These weren't random scratchings, but deliberate, controlled motions that suggest the presence of jointed limbs and sophisticated muscular coordination systems. The appearance of monomorphicness traces adds another layer to our understanding of late Ediacaran innovation. These simple, straight trails might seem unremarkable at first glance, but they represent something revolutionary: the evolution of sustained directional movement. Unlike the meandering paths left by earlier organisms, these traces show evidence of purposeful navigation towards specific goals. Even more fascinating are the planolites' traces, horizontal burrows that snake through sediment layers with remarkable consistency. The organisms creating these tunnels had developed the ability to maintain stable depths while moving laterally through the substrate, a behavior that required sophisticated depth perception and positional awareness. But perhaps the most telling traces are those that show evidence of behavioral modification based on substrate conditions. Some burrow systems become deeper and more complex in areas with higher organic content, while remaining shallow and simple in nutrient-poor regions. This suggests that late Ediacaran organisms had evolved the cognitive capacity to assess environmental quality and adjust their behaviors accordingly. The metabolic innovations required to support these complex behaviors were staggering by Ediacaran standards. Active burrowing through sediment demands enormous energy expenditure, far exceeding the metabolic requirements of passive filter feeding or osmotrophic nutrition. Organisms had to evolve more efficient respiratory systems, enhanced circulatory networks, and sophisticated energy management strategies. Oxygen extraction became a critical challenge for active organisms living in environments where dissolved oxygen levels were often marginal. Some creatures developed enhanced gill structures with increased surface areas for gas exchange. Others evolved more efficient oxygen transport proteins that could extract maximum benefit from limited oxygen supplies. The circulatory systems that evolved during this period were marvels of biological engineering. Unlike the simple diffusion-based transport systems that had sufficed for earlier organisms, these new creatures required active pumping mechanisms that could maintain circulation throughout complex, elongated body plans. Heart-like structures began to appear, simple at first but representing a fundamental shift toward active fluid transport. These primitive pumping organs had to coordinate their contractions with the muscular activity involved in locomotion and feeding, requiring sophisticated neurological control systems. Blood-like transport fluids evolved to carry dissolved gases, nutrients, and waste products more efficiently than simple body cavity fluids. Some organisms developed respiratory pigments that could bind oxygen molecules and release them where needed, dramatically improving the efficiency of internal gas transport. The waste management challenges faced by these active organisms were unprecedented in Earth's history. High metabolic rates produced correspondingly large quantities of toxic waste products that had to be removed from body tissues before they could cause damage. Primitive kidney-like structures evolved to filter harmful compounds from circulatory fluids and concentrate them for elimination. Nitrogen metabolism became particularly important as organisms began consuming protein-rich foods and breaking down their own tissues during periods of stress or growth. The evolution of efficient ammonia excretion systems allowed creatures to process nitrogen-containing compounds without poisoning themselves. pH regulation emerged as another crucial physiological challenge. The increased metabolic activity of late Ediacaran organisms produced acids that could disrupt cellular function if not properly buffered. Sophisticated chemical buffering systems evolved to maintain stable internal pH, despite fluctuating metabolic demands. Temperature regulation became increasingly important as organisms developed higher metabolic rates that generated significant internal heat. While these early creatures couldn't actively control their body temperature like modern warm-blooded animals, they did evolve behavioral and physiological mechanisms for avoiding dangerous temperature extremes. Some organisms developed the ability to seek out thermally favorable microenvironments within their habitats. Others evolved metabolic strategies that allowed them to remain active across wider temperature ranges than their predecessors. The sensory revolution that accompanied these physiological advances was equally remarkable. Vision systems evolved from simple light-sensitive spots to complex structures capable of forming basic images. These early eyes couldn't match the sophistication of modern visual systems, but they provided crucial advantages in detecting moving objects and navigating three-dimensional environments. Compound eye structures began to appear, with multiple light-sensitive units that could detect movement across wide visual fields. While the resolution of these early visual systems was limited, they were perfectly suited for detecting the approach of predators or the movement of potential prey. Some organisms developed specialized photoreceptors tuned to different wavelengths of light. This spectral sensitivity allowed them to distinguish between different types of objects based on their optical properties, providing enhanced capabilities for food recognition and predator detection. The integration of visual information with other sensory inputs required significant advances in neurological processing power. Visual centers evolved within primitive brain structures, creating dedicated circuits for analyzing and responding to optical information. Chemical sensing capabilities reached new levels of sophistication as organisms evolved specialized receptor systems for detecting specific molecular compounds. These chemoreceptors could distinguish between hundreds of different chemical signatures, allowing creatures to identify food sources, recognize potential mates, and detect approaching dangers. Taste and smell became distinct sensory modalities as organisms developed specialized receptor organs optimized for different types of chemical detection. Contact chemoreceptors evolved for assessing food quality, while distance chemoreceptors provided early warning systems for environmental threats. The molecular recognition capabilities of these chemical sensors were remarkably precise. Some organisms could detect pheromone concentrations at levels equivalent to a few molecules per litre of seawater, sensitivity that rivals modern analytical instrumentation. Mechanosensory systems evolved to detect mechanical stimuli with unprecedented precision. Pressure-sensitive cells could distinguish between different types of mechanical contact, allowing organisms to differentiate between substrate contact, water currents, and contact with other organisms. Vibration detection systems emerged that could sense mechanical disturbances transmitted through water or sediment. These capabilities provided early warning systems for approaching predators and allowed organisms to detect the movements of potential prey, even when visual contact was impossible. Some creatures developed lateral line-like systems that could detect water movements and pressure changes associated with the swimming motions of other organisms. These hydrodynamic sensors provided three-dimensional awareness of nearby activity that was crucial for both predator avoidance and prey capture. The neurological complexity required to integrate all these sensory inputs was extraordinary by pre-Cambrian standards. Centralized processing centers evolved that could combine information from multiple sensory sources and generate coordinated behavioral responses. Primitive brain structures appeared that contained specialized regions for processing different types of sensory information. Visual processing centers, chemosensory integration areas, and mechanosensory analysis regions developed distinct anatomical organization that allowed for more efficient information processing. Memory formation capabilities evolved that allowed organisms to store and retrieve information about environmental conditions, successful feeding locations, and dangerous situations. These cognitive advances enabled learning behaviors that could improve survival and reproductive success over time. Decision-making processes became more sophisticated as organisms developed the ability to weigh different types of information and select optimal behavioral responses. Simple cost-benefit analysis capabilities allowed creatures to make better choices about energy expenditure, risk assessment, and resource allocation. The behavioral repertoires that emerged from these neurological advances were remarkably complex for such ancient organisms. Hunting behaviors evolved that involved sophisticated prey detection, stalking strategies, and capture techniques that required precise coordination between sensory systems and motor responses. Some predators developed ambush strategies that involved remaining motionless until prey approached within striking distance. Others evolved active hunting techniques that required sustained pursuit and capture of mobile prey organisms. Prey capture mechanisms became increasingly sophisticated as predators evolved specialized anatomical structures for grasping, immobilizing, and consuming other organisms. Primitive jaws, grasping appendages, and injection systems appeared that could effectively subdue struggling prey. Feeding behaviors diversified to exploit different types of food resources with maximum efficiency. Some organisms specialized in processing specific types of prey, developing anatomical and behavioral adaptations optimized for particular feeding strategies. Defensive behaviors evolved in response to increasing predation pressure, as organisms developed sophisticated strategies for avoiding, deterring, or escaping from potential predators. Hiding behaviors became more complex as creatures learned to identify and utilize protective microhabitats. Escape responses evolved that could be triggered by specific sensory cues associated with approaching predators. These behaviors required rapid coordination between sensory detection systems and motor response mechanisms that could generate effective evasive maneuvers. Warning systems developed that allowed organisms to communicate danger to conspecifics through chemical signals, mechanical vibrations, or visual displays. These early communication behaviors represented important steps toward the complex social interactions that would characterize later animal groups. Territorial behaviors emerged as resources became more limited and competition intensified. Some organisms developed the ability to establish and defend specific areas against competitors, using aggressive displays, chemical marking, or physical confrontation to maintain exclusive access to valuable resources. Reproductive behaviors became increasingly elaborate as organisms evolved sophisticated mechanisms for finding suitable mates and ensuring successful reproduction. Courtship displays developed that allowed individuals to assess potential mate quality and demonstrate their own fitness. Mating systems became more complex as organisms developed strategies for maximizing reproductive success under different environmental conditions. Some species evolved elaborate courtship rituals that required significant time and energy investment, but resulted in higher quality offspring. Parental care behaviors began to appear as organisms invested more resources in protecting and nurturing their developing young. These behaviors required sophisticated recognition systems for identifying offspring and complex behavioral programs for providing appropriate care. The construction behaviors that evolved during this period were equally remarkable. Some organisms developed the ability to build complex three-dimensional structures that provided protection, enhanced feeding opportunities, or improved reproductive success. Tube construction became increasingly sophisticated as organisms evolved better techniques for secreting and shaping protective shells. Some species developed the ability to incorporate foreign materials into their constructions, creating composite structures with enhanced strength and durability. Burrow architecture reached new levels of complexity as organisms learned to create multi-chambered systems with specialized areas for different activities. Some burrow systems included feeding chambers, waste storage areas, and protected nursery spaces for developing offspring. Colonial construction behaviors emerged as some organisms developed the ability to coordinate their building activities with conspecifics. These early examples of cooperative construction created larger, more complex structures than any individual could build alone. The biomineralization technologies that evolved during the latest Ediacaran represented some of the most sophisticated biochemical innovations in Earth's history up to that point. Organisms developed precise control over crystal nucleation, growth, and organization that allowed them to create structures with specific mechanical properties. Calcium carbonate processing became increasingly refined as organisms evolved specialized cells for extracting calcium ions from seawater and organizing them into ordered crystal structures. These biomineralization systems required sophisticated organic templates that could guide crystal formation with remarkable precision. Some organisms experimented with different crystal forms of calcium carbonate, producing structures with varying mechanical properties optimized for different functions. Calcite constructions provided maximum strength for protective applications, while aragonite structures offered greater flexibility for growth and repair. Silica biomineralization appeared in some lineages as organisms developed alternative approaches to constructing hard parts. Siliceous structures offered different advantages than calcium carbonate, including enhanced resistance to dissolution and unique optical properties. The organic components of biomineralized structures became increasingly sophisticated as organisms evolved specialized proteins and polysaccharides that could control crystal formation with extraordinary precision. These organic matrices determined crystal orientation, size, and morphology in ways that optimized structural performance. Composite construction techniques emerged as organisms learned to combine different materials into structures with superior mechanical properties. Some constructions incorporated both organic and inorganic components in layered or fiber-reinforced arrangements that provided enhanced strength and toughness. The energy costs associated with biomineralization were enormous, requiring organisms to develop enhanced metabolic capabilities and efficient resource acquisition strategies. The evolution of these construction behaviors represented major commitments of biological resources that had to provide corresponding survival advantages. quality control mechanisms evolved that allowed organisms to monitor and repair their biomineralized structures as they developed. Some species could detect defects in their constructions and implement corrective measures to maintain structural integrity. The physiological integration required to coordinate all these complex biological systems reached unprecedented levels during the latest Ediacaran. Organisms evolved sophisticated regulatory networks that could maintain homeostasis while supporting the energy demands of active lifestyles. Hormonal communication systems began to appear that allowed different parts of the organism to coordinate their activities through chemical messaging. These early endocrine systems provided mechanisms for integrating metabolic processes, growth patterns, and behavioral responses. Feedback control mechanisms evolved that could adjust physiological processes based on changing environmental conditions or internal requirements. These regulatory systems allowed organisms to maintain optimal performance across varying circumstances. The developmental programs that guided the construction of these complex organisms became increasingly sophisticated as genetic regulatory networks evolved to control the precise timing and spatial organization of anatomical development. Gene expression control systems developed that could activate different sets of genes in response to developmental cues or environmental signals. These regulatory mechanisms allowed for the construction of complex body plans with specialized tissues and organs. Cell fate determination processes became more precise as organisms evolved better mechanisms for directing different cell types along specific developmental pathways. This cellular specialization enabled the construction of complex organ systems with enhanced functional capabilities. Morphogenetic processes evolved that could shape developing tissues into complex three-dimensional structures through coordinated cell movements and shape changes. These developmental mechanisms were essential for constructing the elaborate anatomical organizations that characterize late Ediacaran organisms. The ecological interactions that emerged from all these biological innovations created ecosystem dynamics of unprecedented complexity. Predator-prey relationships introduced new selective pressures that drove rapid evolutionary change in both offensive and defensive capabilities. Competition intensified as organisms developed more effective strategies for acquiring limited resources. This competitive pressure favored innovations in sensory capabilities, behavioral flexibility, and resource exploitation efficiency. Symbiotic relationships began to develop as organisms discovered that cooperation could provide mutual benefits that exceeded what either partner could achieve alone. These early examples of biological cooperation laid the groundwork for the more complex symbiotic systems that would emerge in later periods. Ecosystem engineering activities became more sophisticated as organisms developed greater capabilities for modifying their environments. The construction of complex burrow systems, reef structures, and other biological modifications created new types of habitat that supported increased biodiversity. Nutrient cycling processes were transformed by the activities of these new organisms. Enhanced bioturbation accelerated the mixing of sediment layers and increased the efficiency of nutrient exchange between different environmental compartments. Energy flow patterns became more complex as organisms developed diverse feeding strategies and trophic relationships. The evolution of predation created new pathways for energy transfer that increased the efficiency of ecosystem energy utilization. Population dynamics became more complex as organisms evolved sophisticated reproductive strategies and life history patterns. The interactions between birth rates, death rates, and environmental variability created complex population fluctuations that influenced ecosystem stability. Community structure became more hierarchical as organisms developed different degrees of ecological specialization and resource requirements. These structural changes created more stable and resilient ecosystem organizations that could persist through environmental perturbations. The biogeochemical impacts of these biological innovations were profound and global in scope. Enhanced biological activity altered the cycling of carbon, nitrogen, phosphorus, and other essential elements through marine ecosystems. Carbonate chemistry was significantly affected by the evolution of biomineralization as organisms began extracting large quantities of calcium and carbonate ions from seawater. These biological activities created local and regional changes in ocean chemistry that influenced the survival and distribution of different organism types. Oxygen cycling was altered by changes in organic matter production, consumption, and burial associated with the new biological activities. The enhanced bioturbation of seafloor sediments affected the efficiency of organic carbon burial and influenced atmospheric oxygen levels. Nitrogen cycling was transformed by the evolution of more complex metabolic pathways and waste production systems. The increased protein metabolism associated with predatory lifestyles altered the production and cycling of nitrogen-containing compounds in marine environments. Phosphorus availability was enhanced by the bioturbation activities that brought buried phosphorus-bearing minerals back into circulation. This nutrient enrichment may have helped fuel the biological innovations that were transforming marine ecosystems. Sulfur cycling was affected by changes in sediment chemistry and biological activity associated with enhanced bioturbation. The mixing of oxygen-rich surface sediments with deeper anoxic layers created new chemical environments that influenced sulfur compound transformations. The trace element chemistry of marine environments was altered by biological activities that concentrated or redistributed various metallic elements. Some organisms developed capabilities for sequestering specific trace elements that were required for their metabolic processes. Isotopic signatures in marine sediments reflect these biological innovations through changes in the ratios of different isotopes of carbon, nitrogen, sulfur, and other elements. These geochemical fingerprints provide detailed records of how biological processes were evolving during this crucial transition period. The environmental feedback effects of these biological innovations created complex interactions between organisms and their physical environment. Enhanced weathering rates increased the flux of nutrients from terrestrial to marine systems, potentially fueling further biological diversification. Climate effects may have resulted from changes in the efficiency of carbon dioxide removal from the atmosphere through enhanced biological activity and carbonate precipitation. These climate feedbacks could have influenced the environmental conditions that shaped further evolutionary development. Ocean circulation patterns may have been affected by changes in the density and chemistry of seawater associated with biological activities. These physical changes could have influenced nutrient distribution patterns and created new environmental gradients that shaped biological evolution. Sedimentary processes were fundamentally altered by the evolution of bioturbation as organisms began systematically churning through seafloor deposits. These activities changed sediment fabric, porosity, and chemical properties in ways that influence preservation conditions and habitat characteristics. The global synchrony of these changes indicates that the biological innovations of the latest Ediacaran were responding to planetary-scale environmental drivers rather than isolated local phenomena. The coordination of evolutionary changes across different continents and ocean basins suggests that fundamental shifts in Earth system processes were creating similar selective pressures worldwide. As we stand at the threshold between the Ediacaran and Cambrian worlds, we can see that this transition represented far more than just the replacement of one set of organisms by another. It marked the emergence of entirely new principles of biological organization that would govern ecosystem function for the next 500 million years. The organisms that successfully navigated this evolutionary gauntlet possessed a remarkable toolkit of capabilities that would prove essential for thriving in the more complex and competitive world that was emerging. They had developed mobility, sensory sophistication, behavioral flexibility, physiological integration, and the ability to construct and maintain elaborate biological structures. Most crucially, they had learned to exploit the opportunities created by conflict and competition rather than simply enduring environmental challenges passively. The peaceful coexistence that had characterized much of the Ediacaran world had given way to dynamic ecosystems where innovation, adaptation, and competitive success became the primary drivers of evolutionary change. The innovations that crystallized during these final Ediacaran moments would provide the technological and organizational foundation for virtually every major advance in animal evolution over the subsequent geological epochs. From the fundamental principles of biomineralization to the basic architecture of complex nervous systems, from sophisticated sensory capabilities to elaborate behavioral repertoires, the late Ediacaran pioneers established the biological infrastructure that would support all future evolutionary experimentation. And so the ancient world prepared for its final metamorphosis, unaware that it was about to witness one of the most spectacular explosions of biological creativity in the entire history of life on Earth. The innovations were in place, the selective pressures were mounting, and the stage was set for the Cambrian revolution that would transform our planet forever. The Ediacaran experiment was reaching its crescendo, and what came next would exceed even the remarkable achievements of these pioneering ecosystems. The age of complex animal life was about to dawn, built upon the extraordinary foundation laid by the visionary organisms of the Ediacaran world. The morning of the Cambrian period didn't arrive with fanfare or ceremony. There was no dramatic moment when the last Ediacaran organism took its final breath, and the first Cambrian creature opened its eyes. Instead, it unfolded like the gradual brightening of dawn, where each passing moment revealed new details of a world that had been quietly transforming itself, while ancient empires crumbled into memory. What strikes me most about this transition is how it reveals something profound about the nature of evolutionary change. We often imagine evolution as a steady climb up a mountain of complexity, but the Ediacaran-Cambrian boundary shows us something different. It shows us evolution as an explosion of experimentation, a biological renaissance where life suddenly discovered that the rules it had followed for millions of years were merely suggestions, not commandments. By 538 million years ago, the trace fossil record tells a story of unprecedented innovation. Cruciana trackways become more elaborate, showing evidence of organisms with increasingly sophisticated appendage arrangements and coordination systems. These weren't simple scratch marks anymore. They were signatures of creatures that had mastered the art of controlled movement through three-dimensional space. The bilateral symmetry that had begun to emerge during the late Ediacaran now dominated marine ecosystems. This wasn't just an aesthetic preference. Bilateral organization provided the architectural foundation for directional movement, concentrated sensory systems, and the development of distinct head and tail regions that would prove essential for active lifestyles. Head regions became command centers where sensory organs clustered around primitive brain structures. These neurological control systems could process environmental information and coordinate complex behaviors in ways that would have been impossible with the diffuse nervous networks of earlier organisms. The concentration of sensory organs in head regions created the first examples of cephalization, a trend that would become one of the defining characteristics of animal evolution. Eyes, chemoreceptors, and mechanosensors packed into specialized head capsules that could gather environmental information with unprecedented efficiency. Visual systems reached new levels of sophistication as compound eyes evolved with hundreds or even thousands of individual optical units. These early visual systems couldn't match the resolution of modern animal eyes, but they provided crucial capabilities for detecting movement, recognizing shapes, and navigating complex three-dimensional environments. Some organisms developed specialized visual systems tuned to different lighting conditions. Deep water forms evolved enhanced light sensitivity that allowed them to function in dim environments, while shallow water species developed systems optimized for bright variable lighting conditions. Color vision began to emerge as organisms evolved photoreceptors sensitive to different wavelengths of light. This capability provided enhanced discrimination between different types of objects and may have played important roles in prey recognition predator detection, and mate selection. The integration of visual information with other sensory inputs required significant advances in neurological processing capabilities. Visual centers, within primitive brain structures, developed specialized circuits for analyzing movement, recognizing patterns, and coordinating visual information with motor responses. Chemical sensing reached extraordinary levels of sophistication as organisms evolved receptor systems capable of detecting and discriminating between thousands of different molecular compounds. These chemoreceptors could identify food sources, recognize potential mates, detect territorial markers, and provide early warning of approaching predators. Olfactory systems became specialized for detecting airborne or waterborne chemical signals at great distances. These distance chemoreceptors could track chemical trails, locate food sources, and monitor environmental conditions across large spatial scales. Taste systems evolved for direct chemical analysis of potential food items or substrate materials. These contact chemoreceptors could assess nutritional quality, detect toxins, and guide feeding decisions with remarkable precision. The molecular recognition capabilities of these chemical sensors approached the sensitivity of modern analytical instruments. Some organisms could detect pheromone concentrations at levels of parts per billion, sensitivity that allowed for complex chemical communication systems. Mechanosensory systems evolved to detect an enormous range of mechanical stimuli with extraordinary precision. Pressure sensors could distinguish between different types of substrate contact and assess the mechanical properties of potential food items or construction materials. Vibration detection systems became sophisticated enough to analyze the frequency, amplitude, and direction of mechanical disturbances transmitted through water or sediment. These capabilities provided three-dimensional awareness of environmental activity that was crucial for both predator avoidance and prey detection. Flow sensing systems evolved that could detect water currents, pressure gradients, and hydrodynamic disturbances associated with the movement of other organisms. These sensors provided continuous environmental monitoring that enhanced survival in dynamic aquatic environments. The neurological integration of all these sensory inputs required brain structures of unprecedented complexity. Centralized processing centers evolved with specialized regions for analyzing different types of sensory information and coordinating appropriate behavioral responses. Memory systems became more sophisticated as organisms developed enhanced capabilities for storing and retrieving information about environmental conditions, successful feeding strategies, and dangerous situations. These cognitive advances enabled learning behaviors that could improve performance over time. Decision-making processes evolved that could evaluate multiple types of information simultaneously and select optimal behavioral responses based on complex cost-benefit analyses. These cognitive capabilities allowed organisms to make sophisticated choices about energy allocation, risk assessment, and resource exploitation. Motor control systems reached new levels of precision as organisms evolved sophisticated mechanisms for coordinating complex movements. Muscular systems became more elaborate, with specialized muscle groups for different types of locomotion and manipulation activities. Locomotion strategies diversified as organisms evolved different approaches to movement through aquatic environments. Swimming techniques became more efficient through the development of streamlined body shapes and sophisticated propulsion mechanisms. Crawling behaviors became more coordinated as organisms developed jointed appendages and sophisticated coordination systems. These terrestrial locomotion capabilities opened up new habitat opportunities and resource exploitation strategies. Burrowing techniques became increasingly sophisticated as organisms evolved specialized digging appendages and behavioral strategies for excavating complex, three-dimensional tunnel systems. These subterranean lifestyles provided protection from predators and access to buried food resources. Climbing capabilities evolved in some lineages as organisms developed appendages and behavioral strategies for navigating three-dimensional habitat structures. These arboreal skills allowed exploitation of vertical habitat space and resources unavailable to strictly benthic organisms. The feeding strategies that emerged during the early Cambrian represented a quantum leap in biological sophistication. Predatory behaviors became highly specialized as organisms evolved anatomical structures and behavioral techniques optimized for capturing and consuming specific types of prey. Grasping appendages evolved with sophisticated joint mechanisms and muscular control systems that could manipulate objects with remarkable precision. These manipulative capabilities enabled complex food processing behaviors and tool use activities. Cutting and crushing structures appeared that could process tough or hard-shelled prey items. These feeding appendages required precise muscular control and sophisticated sensory feedback systems to operate effectively. Injection systems evolved in some predatory lineages that could deliver toxins or digestive enzymes to subdue prey organisms. These chemical weapon systems required specialized glands, delivery mechanisms, and sophisticated behavioral coordination. Filter feeding techniques became more efficient as organisms evolved elaborate filtration structures and pumping mechanisms. These feeding systems could process large volumes of water and extract nutrients with remarkable efficiency. Deposit feeding strategies became more sophisticated as organisms evolved better mechanisms for processing sediment and extracting organic particles. These feeding techniques required complex digestive systems and sophisticated behavioral strategies for identifying productive feeding areas. Scavenging behaviors became more specialized as organisms evolved enhanced capabilities for locating and processing dead organic matter. These ecological roles required sophisticated chemical sensing systems and behavioral strategies for competing with other scavengers. The defensive strategies that evolved in response to increasing predation pressure were equally remarkable. Armor systems became more elaborate as organisms developed sophisticated biomineralization techniques for constructing protective shells and plates. Spiny projections evolved that could deter predators through mechanical deterrence. These defensive structures required precise biomineralization control and sophisticated integration with locomotion and feeding systems. Camouflage strategies appeared as organisms evolved capabilities for matching their appearance to environmental backgrounds. These concealment techniques required sophisticated behavioral control and may have involved the first examples of active color change. Escape responses became more rapid and coordinated as organisms evolved enhanced muscular systems and neurological control mechanisms. These evasive behaviors could be triggered by specific sensory cues and executed with remarkable speed and precision. Warning systems evolved that could alert conspecifics to approaching dangers through chemical signals, mechanical vibrations, or visual displays. These communication behaviors required sophisticated signal production and reception capabilities. Group defensive behaviors began to appear as organisms developed the ability to coordinate their defensive responses with conspecifics. These early examples of collective defense represented important steps toward more complex social organizations. The reproductive innovations that emerged during the early Cambrian were equally sophisticated. Courtship behaviors became more elaborate as organisms evolved complex behavioral displays for attracting mates and assessing partner quality. Mating systems became more diverse as different species evolved strategies optimized for their specific ecological circumstances. Some developed elaborate tournament behaviors where males competed for access to females, while others evolved cooperative mating systems with shared parental responsibilities. And so we reach the end of our journey through the Ediacaran world, a chapter in Earth's history that reads more like science fiction than science fact. From the fractal pioneers of the Avalon explosion to the competitive innovators of the Nama assemblage, we've witnessed the rise and transformation of our planet's first complex ecosystems. These weren't just biological curiosities or evolutionary footnotes. They were the architects of everything that followed, the visionaries who proved that life could be more than mere survival. Tonight, As you look around at the world surrounding you, remember that every ecosystem, every food web, every predator-prey relationship traces its lineage back to those ancient seas where ranger morphs swayed in the currents and Dickinsonia glided across microbial mats. The Ediacaran world may be gone, but its legacy pulses through every heartbeat, every breath, every moment of complex life on Earth. Thanks for joining me on this incredible journey through deep time. If this exploration of our planet's most alien chapter fascinated you as much as it did me, hit that like button and let me know in the comments what other prehistoric worlds you'd like to explore together. The story of life is far from over, and there are so many more ancient mysteries waiting to be discovered.